Thank you, Teho, for that introduction. Good morning, everyone. My name is Jermaine, as per the introduction. I'm going to talk about QA/QC programs and the role of certified reference materials in QA/QC programs. Today's presentation, we'll look at what quality control and quality assurance and quality control actually is, the importance of quality assurance and quality control in mining as a whole, the importance of certified reference materials in QA/QC programs in geochem laboratories. We'll look at quality control samples particularly, analytical bias, equipment calibration, analytical method validation, and just have a bit of a recap again on the role of QA/QC in general. Because there's a lot of students here today, because there's a lot of students also available today, I thought it's good to actually look at what quality control is in the broader aspect of it. Mining is a really big undertaking, and the principal reason for mining is that we need the commodities for practical uses. There's a mined material in almost everything that we use today, from the planes in which we fly into some of the water bottles that we use in our cars, in our phones. There is not a mined material. There's very few things without a mined material in there. Mining is obviously a very contentious area as it is of economic importance and therefore political interest, but also it is very environmentally taxing. We therefore have to conduct the entire mining process in the most sustainable way. The way in which that is done is a quality assurance and a quality control program throughout the mining value chain. So what is it specifically? Quality assurance and quality control are two major components of any quality management system. And we know quality management systems apply almost in any industry. ISO specifically defines quality assurance as the assembly of all planned and systematic actions necessary to provide adequate confidence that a product, process, or service will satisfy given quality requirements. And it defines QC or quality control to a system of activities to verify the quality control activities are effective. While QA deals with the preventions of problems, QC aims to detect the events in which errors occur. So essentially, in our office, we have like a I don't want to call it a standing joke, but we joke about it because our quality specialist is very pedantic about these things, about when a non-conformance occurs, then there's obviously, and that might be a mistake or an appeal or whatever it is, and you have to raise a non-conformance, and when the non-conformance is raised, then you have to come up with a preventative action if the preventative action is not in that. And obviously there needs to be systems to detect the systems that you have in place, if they are working or not. So you can really see how, in general, quality control refers to a set of quality assurance and quality control refers to a set of SOPs and the measures in which you put in there to actually test if these things are working or not. So from a mining perspective or mining value chain in general, what is very important is accuracy and reliability, compliance, reputation, cost effectiveness of a QC program, or that it can prove that. And obviously then the continuous improvement, and again, continuous improvement is something that, and it's also something we joke about a lot, but not in a negative way, more like we want to add value in continuous improvement. We don't want to just do things for doing things. But from an accuracy and reliability perspective, QC program in the mining industry, mining is a highly precise and technical field, and the QC programs there should help ensure that the data collected is accurate, reliable, and consistent. This helps reduce the risks of errors and mistakes that could lead to costly problems down the line. With regards to compliance in mining, mining companies are required to comply to a range of regulations and standards, including safety regulations, environmental regulations, and reporting requirements. A QC program helps there to ensure that the company is meeting these requirements and that the operations are safe and environmentally responsible. From a reputational point of view, mining companies operate in communities, and their reputation is always important. A QA/QC program can help build trust with stakeholders by demonstrating that the company is committed to producing high quality products and operating in a responsible manner. And we know from our recent history that, our interaction from a mining perspective with our communities have not been that great. For cost effectivity, a well-designed QA/QC program can help mining companies identify and address issues early on before they become more costly to fix. This can result in significant cost savings over time. And then from a continuous improvement, this could be anything. A QA/QC program can help mining companies continuously improve their operations by identifying areas for improvement and implementing changes to address them. This can lead to increased efficiency, productivity, and overall profitability. So we can see that QA/QC programs applies throughout the mining value chain, but as a certified reference producer, I will focus on QA/QC programs in analyzing all but materials in the geochemistry laboratory environment. A thorough QA/QC program in a mineral laboratory should include specific procedures and protocols that are tailored to the unique requirements of mineral analysis. Key components of a QA/QC program for a mining laboratory should include sample handling and preparation, quality control samples, calibration and verification of equipment, method validation and verification. So these three items, quality control, calibration, and method validation, will be the of discussion for the rest of the presentation. But it should be not be limited to that. Obviously, we should also be QA/QC programs will also include data management, as was discussed yesterday, personnel training, and compliance with regulation and standards. From a sampling and handling perspective, a good QA/QC program should specify procedures of collecting, handling, and preparing mineral samples to ensure their integrity and avoid contamination. This may include label, sealing, storing of samples in appropriate containers, and using specialized equipment for grinding, pulverizing, or homogenizing the samples. From a data management perspective, the program should specify procedures for managing data, including documenting all aspects of the analysis, such as sample preparation, calibration, analysis, and reporting, as was discussed yesterday in almost all of the data management discussions. With regards to personnel training, a program should include processes or procedures of training laboratory personnel in the QA/QC program. So having an overall idea of what the QA/QC program means. So that is generally just, a test through your SOPs, what they actually mean and how they must be implemented and tested, including and handling preparation of samples, operation of equipment, analysis of quality control samples, and data management. And from a compliance perspective, this is obviously big in your mineral laboratories. The program should ensure compliance with the relevant regulation and standards, such as ISO 17025, which outlines the general requirements for the competence of testing and calibration laboratories. So going forward, we'll look at quality control samples, we look at calibration or verification of equipment, and we look at method validation and verification, and what a QA/QC program should look in for those three specifically. For quality control samples, the program should include procedures of analytical quality control samples, such as blanks, duplicates, and standards to monitor the accuracy and precision of the analysis. So this was also discussed or talked about or highlighted a lot yesterday. The idea is to take any form of biases in a lab. An acceptable level of bias is said to be a bias of less than 0.1%, but we obviously know, practically speaking, that's not always possible to achieve, and a discretion is allowed in that sense. To calculate whether control samples have a bias of less than, let's say, 0.1% for the arguments of this discussion, you would need to perform a statistical analysis that compares the test results of the control samples to a known reference value or target value, obviously, an MCRM, I would say. Next, I'll just sort of highlight a generic way to calculate a bias. So what you do is you You collect the data from for control samples and the reference of a target value. You calculate the mean of the control samples, and you calculate the mean value of the reference targets. The difference between those two, obviously divided by or multiplied by 100, will be then expressed as the percentage, and you would then get a good idea what your bias generally will be. So when you look at bias and you receive your results, and you have sent your data to a reference, a laboratory, or whatever it is as part of your procedures, and you see where you fall within, let's say, a set chart. So normally you look at a chart like this. This is a gold analysis by cyanide leach or leach well method. And you can see that here there's only a few labs that reported. So it's lab H, lab I, lab K, and lab P. And you can clearly see that lab H has a significant lower bias. Most of it lies below the mean, whereas for lab H, most of it lies above the mean, but you can see lab lab I actually have more issues with regards to bias for gold analysis than anything else. Lab K and lab P looks like they have high, what we would call precision and accuracy in this case, right? This is also gold analysis, same sample, but here it was done using fire assay with electrical and finish, and you can see more labs reported in this particular incident. And you can see there's lab G, lab R, and you can see most of them actually do report around the mean, but obviously still within the two-step deviation. But you can clearly see which labs have a bias, and you would need a set of protocols to address this in your lab. And that's why your quality assurance and quality control then becomes important again, and you can identify based on the procedures that you set in place for yourself, and talking obviously to your reference material producer, how to address the bias that you are seeing. With regards to calibration and verification of equipment, a QA/QC program should include processes or procedures for calibrating and verifying the accuracy and precision of laboratory equipment, such as spectrometers, your XRF machines, and your atomic absorption spectrophotometers. The calibration of equipment involves verifying and adjusting the performance of analytical instruments used in mineral laboratories. So the process would essentially include the following. You identify a reference standard that you can use. This involves selecting the standard sample with a known concentration and method. Obviously, for Amazon, we can help you if we can. Testing the equipment. The instrument is tested by measuring the signal response of the standard. So again, you're trying to replicate here what standard value would be on your certificate. You compare the results. So here, the measured results are compared to the expected value. So what you have reproduced or what you produced is then obviously looked in contrast to what the standard would be. And then you adjust your instrument. If the measured value are not within acceptable ranges, the instrument are adjusted or calibrated to bring it back to the expected values. Now we're going to look again at the same chart and just speak to calibration. Again, for cyanide leach method, gold analysis, the idea is that your equipment will be able to reproduce, let's say, set analysis, and you can see the gold values on the left-hand side there. So you have to understand now or think, is this detection limit for this particular equipment appropriate for analyzing this particular grade? If not, obviously, then you have to use a different instrumentation. However, there are means of calibrating your equipment using a standard, even though different methods or different equipment were used being analyzed. You have to be able to see if, or there's a test that can be done, again, be part of your system, in which you see is a means. Can I do a means comparison test to see if our means are actually statistically comparable if we are using two different instrumentations, right? With regards to calibration for this particular method here, the same applies. Is the detection limit appropriate for this particular grade at which I am analyzing? If not, then obviously I need to use a different standard. These are obviously low-grade gold standards. And Again, the idea is to reproduce the value. If you can't reproduce the mean specifically, remember it's within a two standard deviation, and I guess depending on the amount of error that's introduced or uncertainties, there's different stats that can be applied to your data in order to accommodate for uncertainties that you might not know about. With regards to method validation, method validation in this particular QA/QC program, we verify that the analytical method used in the mineral laboratory is reliable and procedures and produces accurate results. Method validation typically involves testing a set of samples using the method, analyzing the data, and comparing the results to a reference method or certified reference material. If the results meet the predefined acceptance criteria for each parameter, the method is considered validated and can be used for analysis. The validation process includes several parameters, such as your linearity, which this parameter looks at different concentration levels. Is a method appropriate? So let's say you have you're analyzing for gold at 1 gram per ton, gold at 5 grams per ton, gold at 10 grams per ton. Is the same method appropriate for analyzing at those 3 ton? This is what this parameter refers to. For accuracy, the parameter evaluates how close the measure value is to the true value. So here you're looking at the value that you have produced, how close is it to the mean value? That will talk to your accuracy. From precision, the parameter evaluates the reproducibility of the method by measuring how close the multiple measurements of the samples are to each other. So here you're not really looking at your mean value at all. You're looking at it when you analyze a sample or a CRM, how often do you reproduce the same value or close to the same value, obviously within a standard measure of error. And your specificity. So our instruments are very good today that we can actually say what analytes are being targeted, but specificity refers to the parameters that evaluates how well the method can distinguish the target analyte from other components in the sample. So we're going to look at the same data set here for method validation. Again, here you would look at specifically precision and accuracy, and you can see with lab K and P, there's a high level of accuracy and a high level of precision. So they're good to go, but with lab I, there's obviously a lot going wrong there because you can see where the outliers is. It's outside of the 3SD, and your protocols or your QA/QC program should then be able to tell you exactly what to do in order to correct for that as a laboratory. With regards to lab H, they do have a high bias again, and the accuracy and precision is a bit scattered all over the place. With regards to this method, you can see a lot of labs again have generated data because it's the easier method. But if you look at lab G and lab R specifically, you can see R is here in the corner. There's a high level of precision, but not much accuracy, as you can see. So they were able to reproduce the result. They're still within the 2SD, and it's still passing, but you can see obviously there's a bit of a problem. And with lab G, it sits in that upper quadrant there, and that's also a bit of a problem. But most of the other laboratories, if you can look at them, they are scattered along the mean value and definitely well within the 2 standard deviation. So just to recap again, when looking at a QA/QC program specifically for mineral laboratories, it is a set of protocols and procedures to ensure the quality and reliability of your data and the compliance to a regulatory framework. In mining laboratories, there is a set of standards to comply to in order to provide quality data. From a CRM producer perspective, the major areas of control is obviously quality control samples and the analysis thereof, calibration of analytical equipment, and analytical method validation. So with all these things, you can speak to us directly and we can address certain problems when they occur. We can look at custom making specific standards for you in your area of mining, because that also speaks to your accuracy, precision, and how well your lab actually does in the long run. And these are all things that we can actually do to help your QA/QC program. But ultimately, it's for you guys to, all laboratories, to set up protocols and procedures that they can do to prevent problems from happening and actually just testing how your process in the totality, not only where CRMs are involved, but the totality of your process, how you can set up your standard operating procedures in order to actually get the most reliable results. Guys, thank you for listening, and I hope it was clear what I was saying.
Okay, good morning. Can I be heard?
Yes, we are able to hear you perfectly.
Okay. My talk today is on the practical side of sampling. It's the pieces of sampling that I've done over the last 50 years. Most of the people who are probably listening to me weren't even born when I started working.
Yep.
I've stayed up to date as much as I can. And as the years have gone by, the only difference between the day I started and what happens today is there's such a thing as compliance. When I started, nobody complied with anything. They did their own thing. And a lot of what we do today, we have developed over the years. And I can tell you, we had to fight tooth and nail to get anywhere. And this, for instance, is the mine laboratory at the world's richest gold mine in 1999. Those of you who are in resource estimation may know Vaughan Chamberlain of Anglo Gold. Well, Vaughan and I together spent a great deal of time trying to. Now, that is what Vaughan Chamberlain and I had to deal with in 1999. The mine management of these mines did not understand that the entire mining environment was contaminated. And it was not only the laboratories, it was everything else in the process. So what I'm going to give you to start with is a bit of history of what we went through, because I think there's quite a lot of learning to be taken away from that. But as you can see, this is an old-fashioned mine laboratory that was believed to be functional and doing the job. Well, I've got news for them. If you notice, I say there, we put in 33 silicious Momoni dolomite samples. We had sent them to Australia, where they were analyzed by a low-level gold assay and came back with 0.01 ppb gold. The mine lab at this particular mine came back with 9 grams a ton average on the 33 samples, with the highest value, believe it or not, at 108 grams a ton. These labs had to be shut down, and we did shut them down, but it took 4 years. So that is where my starting point is. I view assay and chemical analysis not as the laboratory only. I've audited probably 350 odd laboratories around the world. And one thing that's, and I've done that for clients who I'm doing the whole project for. And one thing that's become very clear is that the sampling and the laboratory should not be separated in the concept of the mining company. It should be one entity. What often happens when I deal with clients is they send stuff to a laboratory, goes away, they don't question it, and it comes back. And the laboratory, on the other hand, gets these samples and never questions how they were put together or anything. So there's this gap between lab and client as to what the sample is. And this is where I come in, and I've done a lot of work on this to try and get the whole process in the state that the laboratory is in, because we will always audit the labs, but never the sampling process. And this is what I'm going to be talking about. So I've established an effective procedure for auditing the course of assay and sampling process from site to the database. The whole thing is monitored and checked for the client. And this is what I do. And some interesting things have come out of it, and I'll go into this as I go along. But it's an inclusive and holistic data collection policy that I encourage from my clients, and it works. And it improves the quality control by a great deal. And also, errors are not found later in the process when resource estimation is being done. And some resource geologists ask, where was this data collected? You know where it was collected, you know how it was collected, and you know how the samples were taken. Some of these projects are big projects, 400,000 drilling samples. And what the aim is that the first sample taken and the last sample taken in the process of 4 years or 5 years, or however long it takes to drill this program, are comparable. And that's what I try to do. And it requires this whole thing be started early in a program, not late. And it applies to everything, soil sampling, all the way through to the mine. And we'll talk about it. So what we've got here is the way I view geochemistry. It's a process of data acquisition and data management. It includes sampling, chemical analysis, quality control, data management, and databases and interpretation. That's at its most simplest. Those arrows around the slide means that during the entire program, process is being reviewed and recycled and looked at again. so that everything is comparable across the entire process. And what we're going to talk about today is mainly the sampling component. I can talk about chemical analysis for a whole day, but this is the sampling piece. And you'll see that people like Snowden, this is a slide from one of their training courses. If you look over to the left-hand side of that diagram, you'll find that they've got a process: drilling, sampling, logging, assaying, assess database integrity, assess data quality. It's the same thing as what I'm talking about. And there's components of this which will have to be more in mind. I like to look at the scale of things and compare things in the real world. And this is an old diagram. It's divided into two halves. The top half is sampling. The bottom half is what goes on in the labs. And I'm using this diagram because if I produced another one, it would be far too complicated. But the goal is to show two things that happen during this process. There's a significant reduction in sample mass from the moment the sample is taken at the rig to where it's analyzed. In fact, what is happening is something like a 50 to 100 kilogram sample is reduced to a few drops in some of this modern instrumentation. That's all that's analyzed. In the ICP, that's in the plasma nebulizer, a few drops of liquid represent that whole ore body, or a part of that ore body. And the second bit is that the cumulative loss of sample in the process environment, that is the loss of material as you're crushing it, pulverizing it, splitting it, right at the rig all the way across to the end. And that sample loss, in my view, is accumulative and will create biases. So what we try and do is try and minimize that. It's impossible to get rid of it, but I often go into drill rigs and see large pieces of core lying around the drill rig on the ground. That's not on. That means they've lost the client's core. And you go to RC rigs where the situation is even worse. Huge amounts of dust are made. There's no dust control at all. And so this is an example. These are just examples. I can bring pages more. And you go across these various diagrams, you'll see this first one is something I saw during a lab audit a few years ago. And client, another company, their sample bags were calico and they leaked sulfide ore. That's sulfide ore lying in the lab, contaminating every other's client samples. Not only that, their sample loss is controlled by the size of the mesh in that bag. So the fine material is being lost to the bag. That's now going to bias that sample. The next picture is the working place around the pulverizer in a lab. And that is the material that leaked out the pulverizer during the course of pulverization because the seals on the pulverizing dish weren't new, they were worn. But not that they did not collect that material, they just stripped it off that chute and that was the end of it. So a 1 kilogram pulp that started off was probably a 50 to 75 kilogram sample was now losing a fair proportion of its fine material. That can't happen. The next one is a much more unusual project. This is a RC drilling project in soggy, waterlogged laterite. And as you can see, there is just mud everywhere. The sample had to be dry, so they placed them in these pans over to the right of that diagram, and there was just spattering of mud everywhere. Again, sample loss. And the one, we'll come back to that picture, or components of that picture later. There is a cyclone and RC rig with massive amounts of dust being made. That dust is not allowed. That rig must be sealed, both from an environmental point of view and to prevent loss of sample. Whatever dust is generated by an RC rig should be collected and assayed. And then we come to my old enemy, the portable XRF. And we're now talking about sample. And what we have here is a program of sterilization of all Brazilian field officers. As you can see, he's pointing an X-ray gun at the guy's hips. That machine is the X-rays. And this is what concerns me about these instruments. They've been put into the hands of people who are not analysts. Geologists and field officers and field personnel are not analysts. Laboratories take incredible precautions against X-ray poisoning. These guys don't. These machines are unexposed all the way through mines, all the way through plants. Yes, they are 4-watt machines, but they are the problem with radiation is it's cumulative. And I always make sure when I go into site, the first thing I do with these instruments is make sure they're protected. But the next problem with these machines is that no one understands the lower level of detection of analysis. These instruments, lower level detection, is not what the instrument manufacturers claim. It's much higher. I can prove that. I've done dozens of projects. It's not meant for soil sample, as is in this case. So the sample and the method of analysis must match to what you want to do. And so we look at something like XRF in all its components. The portable XRF, first of all, in this diagram is being used correctly. But the sample, as you'll see in the bottom part of the diagram there, is in its original sachet. It hasn't been homogenized. So a proper sample for analysis must be homogeneous, must be representative. So these instruments are often being used to analyze inhomogeneous samples. So the result you get is essentially an assessment, is estimate assay. It's not an accurate one. And if you don't need more than that, so be it. But what is being used for in a lot of cases is cheap soil sampling. And sadly, this instrument does not have the detection limits that allows you to find anything. And the project I've just completed in Botswana for a client, they were trying to use this instrument. They were picking up an anomaly because there were places where the copper that they were looking for was high, but because they weren't doing a multi-element analysis, they did not understand the anomaly, and they had not done any rigorous mapping. So when you're doing something with a specific goal in mind, you've got to do the right things. And the sample includes its environment. That sample comes from a regolith. So therefore you read a regolith map. That is all the environment of the sample. The map, where it comes from. And these samples came out of a drainage in the Kalahari. The receipt wash, it was not visible on the ground. It was visible in a NASA satellite image. We then zoomed out and we discovered that some 16 kilometers away, near Ganzi, was arable land, copper anomalies or copper phosphate fertilizer, which comes from Phalaborwa. And every time I do soil sampling with people, and I get copper, we look for copper, I warn them about soil samples anywhere near farmland. You cannot do copper prospecting near farmland because our phosphate fertilizer is contaminated with copper. And these are things that you need to know about your samples. The next one is the XRF, this wide wavelength dispersive XRF. This instrument is analyzing a highly homogenized sample. Below it is a pressed disc they use. That sample is highly homogenized. Over to the right is the EDS XRF. It is comparable to WDS, but in many instances, the sample is not highly homogenized because it is still in powder form, in other words, it's not pressed. So these small subtleties about how the sample is added to the instrument needs to be understood if you're trying to assess the quality of your assay or analysis. Here is another example, the messiness of fire assay, as we've known, and we will go into small bits of it in a moment. You will see what has happened there. We go through a process of fusion of a rock sample, and we dissolve it in acids, and then we put it in one of these two instruments below, either the atomic absorption in the smaller mine labs or in the big commercial labs in ICP OES. But then our problems with Guy's law and various other aspects of sampling may have been saved by the introduction of photon assay. As is so typical of SARA, and I've worked with SARA, and I know many people at SARA, it's the most impressive organization in Australia. This is the new crisis photon assay. It is developed remarkably from, would you believe it, by a physicist who thought about the X-rays we put through our bodies in hospitals. And that is where this instrumentation started. This is X-rays. And that is a sample size. It's huge. No sample prep is required. And I be quite candid with you, I've not tested the technique. Now, what I would normally do here, I would find a client with money and say, look, guys, I suggest you try this technique, but I would like to test it. Now, I put it through my tests, not the tests that they put it through to make sure that they can sell it. But what I've got here in this particular slide is the claimed advantages of it. First of all, the large samples, whereas fire assay uses 25 grams, this uses 650 grams. There's minimal sample preparation. I crush it to 2 to 3 millimeters. I would actually like to see it crushed a bit finer because I do don't believe 2 to 3 millimeters gets the homogenization that one is required. It's non-destructive. In other words, you can keep the sample in that little plastic bottle and bring it back next week and reanalyze it. The same sample. You can't do that with fire assay. It's rapid. It's 2 minutes per sample versus approximately 70 to 90 samples an hour with fire assay. It has excellent sensitivity. They claim 0.01 ppm on reagent blanks and 0.015, which is about 15 to 30 ppb on gold ores, which is not bad. Fire assay will get you lower than that. With the ICP, you can get 0.01 ppb. So if you really want high quality assay, you still got to high quality analysis. You still got to go to fire assay. And it's independent of the sample matrix, which is wrong, and I'll point that out in a while. I don't think anybody can read the fine print in the orange bit underneath. But what I've got on the right-hand side is comparison of costs with conventional fire assay. They are comparable highly, so I was quite surprised to see that. But there is a problem. You could not analyze Wits ore in it, or any ore with uranium or barium or thorium, because those elements interfere with the X-rays. So those ores, you will not get a reproducible assay with them. So it does have its limitation, which isn't claimed in that blurb. And it's there are the bits that I just mentioned. Time per sample is 2 minutes. Sample size is bigger. Of course, being Australian, I tell you how much of the atmosphere you're polluting in terms of CO2, how much hazardous waste. There's no hazardous waste. I've seen laboratories using the Coupels for making footballs outside the laboratory in the garden. That's lead poisoning. That's lead going into the environment. These fire assays are very polluting and hazardous process, and the energy use is high. And there's what the QA/QC looks like. It's very, very good. We see a bit of a spread towards the lower levels as it is not comparable with gold fire assay. So these are my maxims when I'm out there advising people. You might as well not do a chemical analysis if your sampling is not properly done. And I mean focused and rigorous. The quality of the sample dictates the quality of the analysis, dictates the quality of the project and its value. There's no such a thing as a perfect sample. So you can't take a perfect sample. Your aim is to get as close to perfection as possible. Root sampling requires sustainable and consistent rigor and attention to detail. Now, I'm a consultant, so I have lots of clients and many are junior companies. And I will argue that the high failure rate of junior companies is largely contributed to by inadequate assay process and wanting to spend money on the assay. They don't have enough money, but part of their problem is because they don't really know how to take a sample and be consistent. And I've been onto sites where some of the most horrible things are happening. And it's just wasting their investors' money. And I try very hard to get them to understand. And in many cases, it's very difficult. Because a lot of junior companies are good. Please don't get me wrong. I've got some amazing clients, but many of them are populated by dreamers. And these dreamers are geologists as well. They have this dream of something, and they have a limited amount of money, and they're so determined that they're going to find something. But you can't find it if you don't do the job properly. And they keep on telling you, don't worry, it'll even itself over time. It never does. It never, ever does. So we're going to go back to the early years. Where did I come from with this crazy idea about the sample being so important? Well, my first job, before most of the people listening to me were born, was to investigate gold losses on mining. It made my career, and I learned to understand the Wits gold. Not so much from this point of view, but as a geologist, because I don't have the same idea as how the gold got into the Wits Basin as everybody else does. I don't believe it's a placer. You'll never convince me otherwise. Some of my work in later years also convinced me that my belief in the hydrothermal model may be also erroneous. And at present, I'm busy working on that. There's some strange phenomena in these reefs which nobody has seen unless you look at it in the scanning electron microscope. But anyway, that's beside the point. We found that on blasting in the carbon seam reefs in particular, that between 5 and 35% of the gold particles, if you use the microscopes, this is the big thing. You've got to use microscopes. Nowadays, we didn't have access to the MLAs and the SQUEM scans and the likes. We used the petrographic microscope. And that also has something else. It was my eyes, not instruments detectors, that I see looking the gold grains. So I saw his shape, I saw various other things in them, which also played a role down the line. And I'm not going to mention here, other than in passing, that gold particles are often coated in iron oxide, which inhibited the cyanidation. So we had all these things going together at the same time, because we were looking at it down the microscope. And we're using oil immersion lenses, which allowed us to see around the grain at high magnification. So what came out of this was a program of sweeping of the stopes. And then we checked in afterwards to see what happened. We found that if we pulled up the footwall of the stope, now there's the floor of the stope, and took it back to the laboratory and shook off and weighed everything and shook off all the fine particles, he's found there's still 1 to 5% of the gold in the cracks. So you are losing gold on mining the whole time. And this is where we started to look at the underground sampling as well. And we started to notice that gold was lost between the stope and the plant, suggesting a total loss of gold on mining between 8 and 10%. And over the years, the reasons for the high MCF was investigated, and this became what I called my career civil war. Myself and mining engineers were not from the same planet. The mining engineers running those mines had a mission, which they given mission, and they stuck to it. I had a mission, which to try and help them get better, and to convince them was not easy, because these guys were very focused on the bottom line. And so when you come along and you tell a guy, but guy, you're leaving your 10% of your gold behind on the mine, he doesn't want to know. And I don't blame him. It's how the mines worked in those days. Compliancy requirements are not the same. The power of the resource geologist was not in place yet. And so a lot of things are being done which were not right. And I will maintain that on our gold mines today, the illegal Zama success is possibly due to some of the residue of what was left underground. And I'll show you. So then what we did was we started to pull apart the reef. And these are two examples. On the left-hand side is the VCR, on the right-hand side is the Vaal Reef. And you discovered where there's a carbon seam. All the gold was in the vicinity of the carbon seam. But the VCR, the gold was scattered all over the place. But when we made a microscope section, we could not find a single gold grain that was more than a millimeter away from a carbon globule. There were carbon globules right the way through the reef. So in other words, there are some reefs where the carbon is dissipated all the way through the reef, and the others where it's a single carbon seam. So we focused mainly on the carbon seam reefs because those are the ones which are producing most of the gold. And this is a diagram. This diagram is essentially a face between two sample points. And these two irregular areas like this are 5 meter apart. Those just what are sampling a diagram with one of the sampling channels. We've taken with chisel and hammer. This thing in the middle here is a thing we gave the name of tombstone. Now you can well imagine that I'd take a 100 to 200 kilogram slab of rock out of a gold mine intact. Was quite a piece of engineering, both from the point of view carrying it out and getting the facilities to in a producing mine to carry it out. But we did it. We took many of these things. More than 3/4, in fact, went to Leeds University, where they did completely different work on them. They were looking at the genesis of gold. I was also doing that, but I was also interested in the distribution of gold across the reef. And those little red rectangles are actually thin sections. They're not small thin sections. They are big thin sections. They are, I think, 750 or 550 millimeter thin sections. They're big ones. They made in a special thin section machine called a Logitech. And so they don't fit inside scanning electron microscopes or anything like that. They only fit on the microscope stage. And this is what one of them looks like. This thin section is still in existence. It's in my cupboard at present. It's probably the world's oldest thin section now. But on the left is the actual photograph of the thin section. You can see its size. It was used for many things. Partly that orange rectangle is the origin of the gold, but the other is to map the gold. That is the map on the right-hand side, and that was done for me. I had teams of mineralogists doing this for me. I didn't do much of the work on my own. And those circle sizes, the red ones are 10 grains, the big ones are 25 grains. That's how many grains are in the circle. And you'll see above the carbon seam, we just mapped out that little bit of the whole rock, because we wanted to see if we could find a fluid pathway out for those grains. We did. So many of those grains that are lying in the conglomerate above carbon seam actually have leaked off the carbon seam. That's just a paragenetic thing. But the point is that is what your sample looks like that you're going to take underground. And that particular sample is, there were 4 different sections like it, but you can see what their grades were. Their grades were extremely high. 222, that is the rich part of the gold. And when you blast that, guess what happens? That cracks open and is exposed on mining. So we found that 90 to 98% of gold grains occur within the carbon seam. And this is what it looks like under the microscope. In this particular case, a couple of amazing things. That gold, when it's sampled, is a large amount of gold. That gold, that picture you're looking at there, from the left-hand side, the width of that picture is approximately 2 millimeters. So that is a large particle of gold. Now, what happens when that large particle of gold gets inside the laboratory? It gets inside the pulverizer and is made even larger. So your Guy's law problem gets exacerbated by these wire shapes getting bigger and bigger. That's what happens in the pulverizer. Again, looking at things with a microscope. So we did, there's the microscope. That microscope you see there's in my cupboard. I own it. Anglo gave it to me as a retirement present, which was probably the best thing I've ever was given. I still use it. It's still in good nick. It's been upgraded to 2010 technology, although I now need a new camera. And so I use it on nickel ores, I use it on copper ores. I look at the ore that's being sampled. And out of all this came the mine call factor. I don't know if anyone's familiar with it, but it's a thing that's very much, in my view, specific to the Wits. And we discovered that the value is highest on the carbon seam gold mines. And I, over the years, made a list of what it was, because mine managers just thought it was due to bad sweeping of the stopes. It's not bad sweeping of the stopes. It's inadequate and unrepresentative sampling, and I get to that in a minute. Cumulative gold loss between the stope face and the plant, there's a huge amount of that. We found it in all the drainages, in the sumps, in the sludges at the bottom of the shafts, all over the place. Gold loss in mining was blasted into support areas. At one stage, Western Deep levels had a project where they had something like 40 tons of wood chips, which were brought to the surface in the water. And that stuff ran at gold at grades of about 10 grams a ton. And all they did was incinerate it and get the gold out. So they were recovering some of it. And then, of course, there was gold theft. Now, gold theft is a perennial problem, but the carbon seam reefs, you would often go back into a stope, particularly with this, and on Western Holdings, it's particularly bad, and on Vaal Reefs was bad as well, where you can see they've taken a metal object, probably a nail, 6-inch or 8-inch nail, and they scraped out the carbon seam. And they've also peeled off all the loose remains of the previous blast, which works loose because you get closure underground, so the face starts to collapse. And those things are smuggled away underground where the gold was extracted. So there's a huge amount of gold theft. And how they got it out the mine was the most amazing smuggling exercises known to man. And the other problem, I'll show you a picture of it in a while, backlogs of mined ore underground, shoddy tramming. This is a problem which was never spoken about, but I'll show it to you. Inadequate belt sampling. This is a problem, and it exists in all mines today. The stop and the gold belt sampling doesn't sample the fines. And in the case of the Wits gold, the gold is being liberated on mining. So that fine that lies on the bottom of the conveyor belt is not being sampled. Ore is being sent to waste dumps. And there's an interesting story to tell. I was down in Barkly East last week, on which, and I was standing on a place called T-Krans, which is a huge river valley through which the Kraai River Valley runs, and in it are the famous railway line reverses. All North and Barkly East used to be connected by a railway line. It was last used about 10 years ago. Now the line is defunct. On it were 10 reverses. The mountains are so steep that the train used to reverse up and down the mountains. And all the train watchers used to go there to watch the steam trains. And one of them was a senior geologist, an Anglo-American. And he came to me in the laboratories and he said to me, "Do you know that we found the gold mine?" I said, "Where?" He said, "Where you come from, at Barkly East." I said, "Why?" He said, "Well, we just sampled the ballast on the railway line. And we found it contains up to 12 grams. And I'll never forget to figure 12 grams a ton gold." Did an investigation. We found that the South African Railways was buying waste material from the gold mines, nice Port City gold material to use as ballast in the railway lines. Trouble is that waste material had gold in it. And that is when I was working on that project, I suddenly realized the waste dumps must also be looked at. And we did. We found gold in a lot of the waste dumps. And the next one as well, erratic recoveries in the plant. We found this later. I was doing a project again for another big mining company, trying to assess whether the tailings dams were recoverable. And we put auger holes into them and were sampling every 2 meters. We found some of the samples had far too much gold, way above what we'd expect. In fact, at 2 or 3 grams a ton. And that is because on certain, and there were certain horizons. That is when the plant, the control of what was going on in the plant wasn't what it should have been. And you only found it out years later. No one knew about it. And of course, the contaminated mine laboratories, which I've already shown you. And then the fudge factors used by the survey departments. At one stage, one of our gold mines is 105% iron ore factor, which is impossible. So those are the problems with it. And there is what happened. That is what we call the Madala site, an old stope, hadn't closed yet. So you could get into it and look what had been left underground. That's mined ore. So what do we got? When we got an ore body, which is the bit over here on the left here. And you've got a grid in it. And then you drill it and you sample it, either by something. It's whether it be blast hole, an ore body that you blast hole sampling in the pit, you're diamond drilling because you're exploring it, or RC drilling it, or you're underground sampling it. This stuff arrives in the laboratory in some format, and then it goes all the way through to being digested and fused and whatever else, and it's analyzed in a machine like that. But you start off with a large sample of a couple of tens of kilograms. You reduce it in size to send to the laboratory by splitting and doing various other things to it. But the whole time you're interfering with that sample. And then you fuse it, digest it, eat it up, and put it in a machine. And that little nebulizer takes in a couple of milligrams. In fact, a couple of drops. So there you have your sampling error. As you get out of any paper like Fatard and Dick Minnis papers. And the bits I've highlighted are preparation and analytical errors, where I normally live. And I thought, great. Nobody seems to think this is much of a serious problem. And this is a big problem. Why do we uncouple it here and ignore this bit? So what we did was we took all these various components of the sampling error and looked at them individually and see if we could improve them in any way. Some you can't, some you can. So the fundamental sampling error, which arises from the inherent variability of the material being sampled, you can work on it. And some of these errors can be reduced by maximizing sample mass, reducing fragment size, and minimizing steps. Unfortunately, that interferes with the assay process. And I'm not talking about the modern photon technique. I'm talking about the way things are adjusted. And one of the things that came out of this was this awful piece of machinery here. And many of them were made with a large pulverizer that took anything up to 5 kilograms of material to pulverize. I keep on losing my identities. This pulverizer is far too big. It does not homogenize the sample properly. And when it's so heavy that when it slows down, it de-homogenizes anything. And when we took samples through it, we found particularly with coarse gold, most of the coarse gold had worked its way down to the bottom of the pulverizer, so that it was not homogeneous. This here is fire assay, and as we well know, you cannot make a big sample fire assay. We had people recommending 50 gram, 100 gram assays. That requires increasing the size of the crucible. That also means reducing the number of crucibles you could put into a fire assay furnace, and it also means increasing the fusion time. I've got into labs, particularly lately with orders where they're doing 50 gram samples at the insistence of the client. Those crucibles that you're looking there are designed for a 25 to 30 gram sample. You put in a bigger sample, you need more charge, chances of sputtering and losing material, and inadequate partition of the gold into the lead are increased considerably. So I like, particularly when I'm training people, I like geologists in particular, young geologists, to understand how much we're dealing with if we're doing an assay. And when you normally do, when they sit in the laboratory and they weigh out that material. How much of what you're trying to assay is in that material? Normally at the end of pulverizing, you get a 250-gram pulp in the bag. Well, if you've got a 10-gram sample, do you know how much gold you've got in that little guy? You've got 0.0025 grams. Now you're going to take a spatula out and weigh out 25, 30 grams. So you're reducing that. It's a really small amount of gold. You then digest it, so it does go into solution. So you are homogenizing it by putting it into putting it into solution. But that small amount of gold all get extracted by the lead during the assay. These are things we suspect are always happening and all are right, but it always happen. No, it doesn't. Because the moment you've got high sulfur in your ore, the extraction of the gold is inhibited. So that is why they've often put iron filings or nails or whatever else is old-fashioned assay. They all have it in hand. But it's still, assay is still a messy process. When you do copper or zinc or lead or other base metals, at least it's a direct digestion. Today we use either 2 or 3 or 4 acid digestions. But still remember that 1% copper is 2.5 grams of copper in a 2 pulp. So it's a small amount of material. Another thing to remember is that if 100 micron gold grain, which isn't very big, weighs almost the same as the amount of gold in a sample for 10 gram per ton sample. So that all the gold is in 100 micron grain, you may not get it to assay. The sample will come out to 0. And the 100 micron grain will stay behind because you haven't weighed it out into your 25 gram aliquot. I'll show you that in a minute. So what I did with a lot of the work, again, to try and understand the sampling process, was to look at the gold distribution of particle size under the microscope. I did dozens of these things. And we found that in many cases, particularly in our gold mines and on the Barberton gold mines, and then ultimately on some of the gold mines in all greenstone belts, that's our operations at Sunrise Dam and things like that, that there was a portion of the gold, some of the gold samples that were taken. There was one gold grain that accounted for far too much of the grade. And so what we were doing was actually measuring the grain. Example number 1 was a Varese sample. We measured 1,002 grains and accounted out of 1 grain out of 1,002 grains accounted for 96% of grade. Its diameter was 473 microns. Example 2 shows the distribution of particle sizes. In this, if you've got your right-hand column, which is micron sizes, range of the grains, the number of grains in that size, percentage, then converted to weight using the density of gold. Then there's a weight percentage, and you can see the 400 micron grain in this particular sample, there was only just one grain, 60%. So we've got this problem, plus the fact that the coarse grain gold over on the right here, when crushed, rolls into wires. This is a problem that happens with coarse gold. These are things you need to know about. So then what do we got here? We had a thing we call the mineralogical nugget effect. It's not the same as a nugget effect that's used in geostatistics, but it's a component of it. So what we've got here is a sample in a box, and in it are 2 large gold grains. There are thousands of little ones, and they just get, and you do 30 assays, and they will get into 2 of those assays. The rest will contain trace golds, and 2 will contain gold, what you say is grade. So this is a problem with not understanding your sample. And so we went right back and we went to look at underground sampling. The diagram in the middle is a sketch out of Pittard. And I just put a reef over the top of it, a drawing of a reef over it, and it's got the correct way, 2 channels on the left, the incorrect way. But in fact, the channel on the left, the incorrect way is even more correct than what's actually happening. You'll see on the diagram here, they've drawn chalk lines on the face. This is what they used to do. And then they go in the chisel, and you can see they're taking slabs off. Now the pan, which is in this guy's hand there, is down there. First of all, it's round in shape. So half the sample is falling on the floor. The fundamental rule of sampling is the moment that sample leaves the face, nothing can be lost. No chips can be, because that is what you're taking. Anything that falls off may fall off in an unrepresentative way. And that is what the problem was. And it was terrible. And the big problem is this, is this example in the middle. This is Great Noregwa Gold Mine. That's the carbon seam there. I've just drawn it to make it darker. Now it's sampling down this entire face. So there was channel sampling upwards. And I looked at this thing, and you know how many times out of 10 samples along a face like this, there's 10 or 12 samples, the actual carbon seam actually got into the bag and didn't fall on the floor twice. So they're underestimating the grade. Because that is where 90% of the gold occurs. This is another example from a gold mine I worked on in Fiji, Vatukula gold mine. That area in black, that's a chert. That's got no gold in it, but the tectonized chert above and below the grey material is where the gold is. A whole lot went into the plant, but they never sampled. You see, I put an X here, I sprayed that X on the screen on the face. The whole lot went into the plant, but they discarded that black material from the sample because it had no gold in it. When you're sampling underground, anything that goes into the plant and is associated with the process has to be included in the assay. You can't throw material out at your choice. The next is blast hole sampling. Similar problems arise. What constitutes a blast hole sample? You see this picture here, the 1 second from the left at the top. They're big lumps that come out of the blast hole. Do you leave those behind or put them in the bag? Here, this particular this instrument here, we'll go into this in more detail. This machine has a modern blast hole rig, and they had a thing that looked, they put it into the side of the machine. Material was wet, it was coming out as a slurry. This sample was more reliable, but it was where were big lumps, which they discarded. You cannot discard the big lumps. They are part of the sample. If it lands up in there, it stays in there. And this was a better way of doing it. But you can see here they left the lumps behind. This is another example of a blast hole rig that was set up partly to look a bit like with a cyclone on it. And they split the sample, as you can see, the strange two-way split like this. I don't know how representative it was. The material was very fine grained. And so we have these various issues. Yeah, they're sampling, and on the complete right-hand side, they're sampling, and the material is falling off the side of the spade on the ground. Everything you pick up off the ground is a sample. And it has to be done in a formal way. You can't just shovel it, put it in the bag. So it's cheaper than RC drilling, and you get a better sample density in RC drilling. But in many operations, particularly in Australia, they switch to RC drilling with a cone splitter on the RC rig, and you get a far better sample. It's the practicalities of just making sure that your sample meets what you want to do with it. Because unless sampling is 100% perfect, it's always properly supervised. This is the other issue. Supervision is the big thing, and managing employees are diligent, well-trained sampling teams, which seems to be the case in many places, particularly in Australia, and it was for a while underground in our mines in the later years, where we found that the sampling teams are really well-trained. You're not going to get a good sample. And this is not a gold belt sample, but what I want to show, this is just my example. This is another place where the sample is inadequate because of the practical side of it. This is the belt. We see those fines there on the gold mines. That is not taken with a gold belt sample because it goes over the top of it, and that's left behind. That's got a lot of gold in it, and it's biased in favor of that small fraction. And that is the problem. So this is the world that I've lived in over the last couple of years, and this montage is a sketch of the places I've worked and done things over the years. Diamond drilling operation in Siberia. The Russians do their geology like they do their attacks on foreign countries, not well. And this was a hodgepodge of poor management. The rigs are typical of Siberian rigs. The driller has to sit inside a room because it's cold for most of the year, but they don't look after the equipment. The trays are just thrown all over the place. And they mix up RC drilling holes and diamond drilling holes, and they never can remember which was done where and how. It's not very good. This is a project the DRC will return to this just now. It was well managed, but we had a lot of trouble with the drillers losing equipment. This is an operation in the Andes, drilling for gold. My problem with that particular rig was it was on the side of a cliff. So you had a geological section off to the rig's left, but not to the right. And I could never understand why they put it there. They should have moved it in another 20 meters. over here is an operation in Zambia. That's all diamond drilling. All of that was audited from the moment the sample left the ground to the time it was sent to the laboratory. Here is reverse circulation drilling, similar things. This particular rig here was in Alaska. I would have expected Americans to do a better job than this. This drilling company was fired ultimately. Here we got Sadie Island, Mali. Over here is the rig I showed you earlier. Closer, this is an RC rig. It was used for blast hole drilling. This particular project, I wasn't employed to look at it. I was actually employed to look at the sampling device that was put onto this RC rig. And this is quite a complicated thing. I would rather replace it with a cone splitter, but this is about the most effective sampling device outside the cone splitter I've ever seen. And here's an operation that we had when I was at Uriman looking for uranium near Beaufort West. It's what you see in that picture is a lot better than what it was. That picture was taken at 2:30, 3 o'clock in the afternoon. At 8 o'clock that morning, I was in Joburg, happily sitting at my desk when I was called that they had a problem with the RC rig. It was making dust and the farmers were complaining. And bear in mind how big the Karoo farms are. The farmers, some 10 kilometers away, could see the chimney of dust going into the air. And if you look carefully around the rig, you'll see the ground is white. No RC rig should be doing that. And then we talk about blast hole grade control. All of those samples, the way those samples are taken, I will follow up and check on. So we created an idea to audit a sampling operation the same as you audit a lab. It's based on the approach I use to audit labs. I've done 300 audits in the last 25 years over the whole world. And just as a matter of interest, I will close the laboratory down if I have to. Of the major, and also of the major commercial laboratories, those are the big ones, it's rare that happens. In the one instance that I had to do it, it was in one country. In fact, the two major lab companies, both had a lab in that town, both the labs were bad, both the situation was out of their control, because we went in there and we tried to sort it out together. Because the problem is, and this is North America, it's a difficult country. Because of social issues which we see every day on the news. The drug problems that we had in these labs, drug use, and therefore careless work, was unbelievable. The laboratories were unusual, and the issue both labs sorted the issue out by simply making us transport the labs to Toronto or Vancouver, because we couldn't use those labs. I don't even know if they're open today anymore. So what we're saying is the sampling operations, which mostly can be similarly audited. Now, areas that should be included requires you to understand drilling, both RC and diamond drilling, understand the processes involved, how that material comes to the surface. And the areas that looked at should be all drill rigs, all operation drilling, the drillers and their teams, the workshops, the stores, all core handling, all transport, core marking, measuring, logging, splitting the whole lot. Right through, and now the client takes his sample away from the rig and he starts sampling it, the logging, the QA/QC of core photography, the bulk density measurements, and how the core is stored, what the core yard looks like. This is done to make sure that the material used to do the resource is always in a way that one can go back to, check things up, and make sure that the numbers that we put in a compliance report are actually the real ones, and that they're not only are they the real ones, but they are reflective of what's in the ground. And this is what my goal is. So, as an example, we're going to talk about auditing a diamond drilling operation. The audit is conducted exactly the same way a laboratory audit is undertaken, using a formal audit document. In other words, I've created a document. The full audit documents are conducted by an independent professional. In other words, I would undertaken each project on a regular basis. I don't work or try not to work for the consultancies and do it for them. They should do it by themselves as part of their producing of a competent person's report. They do it independently. I do it for the client because they have got the totality of the project to manage over time. The consultancy company comes in for short periods of time, and often they change. Projects are long, so I try and make sure there's a continuation of the same process that is going to be part of a report. and it works quite well. To be effective, all audits should include a mentoring component. Now, this is done to train the geologists who are rig geologists how to do their job properly, because a lot of this can be done on the rig. So the rig geologists will do less documented audits. They are undertaken on a regular basis. But I found that even there, people become blasé and they don't notice these small things. Small things add up to big things. This is a long process. And every time there's an oversight through the process, it adds up. Like sample loss adds up. You lose a bit here, a bit there. By the time you finished, 50 kilogram sample has lost 5 to 6% of its mass, and you don't know whether that's a biased loss. Well, audit should be undertaken when the project is fully operational. Don't go there when the drillers on holiday. And look at the rigs. No, that must be working. Okay, now just as examples, you look at the condition of equipment, site, environment, safety. I audit the safety in the laboratory the same as I audit. Safety means they are efficient. They are complying to certain standards which they are expected to comply to. It may not affect the quality of the assay, but it does show an attitude. People who are highly follow the correct safety applications are correct. And I've got a picture here where a rig geologist is standing around with his hands on his hips and he's wearing a pair of trainers and not safety boots. It's small things like that you pick up. So you look at the housekeeping around the rig, you look at drill sub management, you look at excess water and mud management, in particular during the rainy season. Rigs during the rainy season, where the heavy rains, need to be monitored because it's more difficult working in that environment. You need to look at the security of the drilling operation. Can anybody just wander in there and fiddle around with your core? Are the personnel protected? Wearing correct PPA? Is the equipment correct? Do they have material to correct oil spillages? Is the core protected from damage from drilling materials? Is there access control to the rig? Not anybody can walk in. The driller's record books must be up to date. Look for safety in the environment, look at the drill rig and the drilling rods. All of that is looked like. These are bits that are taken from one of my auditing pages. You look at the condition of drilling machines, the capacity of the drilling machines. Here are the headings. Condition of drill rods. Excessive grease in drill rods is a problem. And also you need to know the composition of that grease. If you are like today drilling for lithium, just make sure they're not using a lithium-based grease, because that's going to contaminate your sample. You look at the greasing of drill rods. It's important. The condition of drill bits. I look at the unused drill bits, what they've done with them, where they put them, how they store them. Do they have a record of how long they lasted? All that kind of stuff. And then on the right-hand side, you look at the care of the core trays. Now, this is raw material. The loading of the core onto the trays, the labeling of the trays, the core recovery, the measuring of the core. That's a big thing, this measuring of core. I often go there with a tape measure and remeasure and look at stuff. And there's often a couple of millimeters difference, so don't worry about that. But sometimes you've noticed there's a change, suddenly you go from 166 meters to 176 meters and there's no core loss. You've got to make sure that doing everything properly. So when I go to a rig, I look at them, I photograph them. I look at all the signages, the drums, the correct drums, the waste material, fire extinguishers, all of that. I look at them unloading the core. This is done correctly. They're using a triple tube. Exactly how it's done is done correctly. The measurements are done correctly. They're loading the core in the core tray properly. They're not spilling onto the ground. But in this particular case, he's working like this. There's a piece. He's struggling to extract the core from the core barrel. And it's wedged up against the bit. Pieces then fall on the ground. You look at the orange and yellow arrows all around where he's working, and there are little insets around where the cores, bits of core are lying on the ground. Of course, they get walked on those on the bottom left-hand inset diagram. Those have been walked over. Then up on the one side, you'll see the core trays. That's what your core tray should look like, not the mess that's over there on the side. That's one of the things I cleared up on this particular operation. They were using old core trays. You can't do that. Those trays are bent and buckled and rusted. And the driller must look after your trays. You mustn't just throw them around the back of the rig. They must be properly done. And then how it's packed, The diagram in the middle, it's like a little disc. That's how it should be done. And also the bottom right side. We'll get to that in a minute. But all around the other two areas, the tray was lying sort of open in the mud, and there's bits of core. You got core loss, but you've got additional core loss by falling in the mud, and that's it, gone. But you notice the diagram on the bottom left is interesting. There are bits of plastic in the core tray. That's a very useful introduction that I often advise my clients to use. But I check all the use of the little blocks in the core trays, that the measurements are correct. The way these things are made, it's very easy to make a snip up. And so 27 can become 21, and etc., etc. So that I make sure that the abbreviations like cavity are correct. All of that is correct. I've got a little chart I walk around with, which applies to that particular client's core, and I make sure that they stick to that. And there's more core management problems, as you can see during the rainy season. It's a mess. And again, there's other rigs. These aren't the same rigs. Again, the same project, puts a core line around in the mud. And then I go on to transport the core on the left-hand side. That's how core is placed on the back of Land Cruisers. Land Cruisers have got the right size capacity for these things. And you can see everything is done correctly there. And they're bringing them off, they're kept in order, and they're properly stacked on the Land Cruiser when they brought the core yard. That Land Cruiser probably traveled about 15 kilometers over quite nasty roads, bumpy roads. That trip back, those core trays must be strapped down so the core doesn't bounce out of them. I check the core yard and the management of the core. The upper diagram that's how they're supposed to work. It's neat and tidy. The bottom diagram that is the core that's been used. It's accessible at easy time. It's nicely stacked. It's not easy to get out when it's stacked like that, but there are ways and means of doing it. So we then look at the core management and core sampling. The first thing I want to show you is how to deal with core that is broken and falls across the barriers in the core trays. That is what you use. You use strips of plastic. They come in rolls, and you pack the core into it. I'm not overly fond of using plastic in the environment, but it's a problem to make sure that your core integrity and therefore your assay integrity is constant throughout. And then the core photography. There are many ways of photographing core. Companies like ALS and SGS offer brilliant facilities if you don't want to do it yourself. But with a good camera, you can do it yourself. This is an example of it where they photograph the trays both wet and dry. I've been on site where people are using cell phones. Cell phones are used to talk to people on and send WhatsApp messages. They're not used to not designed to do geological work. And the use of cell phones, cameras, I've got good cameras, and I'm not arguing about that. I do the most amazing photography with my phone. But no, this must use specific tools for the job. And then I check and see how they sample the core. The diagram above is from Pittard 1993. That is a standard I would normally use. There's a correct and incorrect way of sampling. Again, I'm not going to go into details of how it's done. All I'm saying is that I audit it. I check to see that sample is laid out correctly. And I will go through the core, how I would sample it and how they sample it. And in many cases, there are small differences. With messy core like this, it's quite obvious that's going to happen. And then I go through the saw. I check to see how many pieces of core are broken off and falling at the bottom of the little sump at the bottom of the saw there. That's more loss. So you're now losing at the rig, you're losing in transit, you're now losing on the saw, and you're losing when you crush it and pulverizing. So every time you're losing a bit. Then I look at how the cores in the core tray. I noticed, for instance, a good core suddenly has broken chips in the middle of it. I want to know what happened there. Was that a core loss? Or why did the core suddenly get broken? So I'll look at the pieces of core. I'll see if it's been recorded or not. If it's been recorded, fair done. In many cases, it's not. Then they put a line down the core where they're going to cut it. They put an arrow to show the core maintains its orientation in the tray. The example I've shown you there is fictitious because I turned the core around just for the photograph purposes. But what I do is I check to see that the core is being placed back in the core trays in the correct manner and is in all the cores the right way around prior to sampling. I check how they cut it, and I go on at the saw, this diagram here where he's got his hands on in the core tray. I see how he does it. In this particular project, Myself and the project geologist trained the core cutting team. There were 2 guys, and they were exceptional. Now, the problem is, how do you cut weathered and broken core? There are dozens of ways of doing it. But this is a technique which I regard, I think a patent will be in fact, it's a technique that I developed. All you need is a piece of scrap sheeting, metal sheeting, and you'll see the line on the top of the core tray there. I've got slots in to put your hands in. The top end is sharpened on a grinding wheel in the workshop or wherever. And you cut the core with it. They actually cut clay core, like lateritic core. You can it cuts it beautifully, and then you just sample on either side of it. When it's broken, like it is on the bottom right-hand side, what do you do then? That's where the problem lies. And there are various ways of doing it. First of all, core is easier. What you do is you use masking tape. Don't use duct tape, because duct tape doesn't come off, leaves a residue. Masking tape doesn't. Use wide masking tape. And you wrap it around the core, and you cut the core with masking tape on it. It stays intact. And those are the kind of sort of practical solutions that I normally come up with things like this. But badly broken core, as in the tray on the right, the sample length must be determined. So in other words, you sample according to predetermined length. You take that entire sample. The large fragments are taken out. They are orientated and split using the saw and returned in the correct position of the tray. That's before you do anything else. The remainder of this, you return the tray after you removed, they're not returned before you do anything else. The remainder of the sample is passed through a riffle splitter. It's a coarse riffle splitter. Anything that doesn't pass through a riffle splitter, you take out and you cut it with a saw in half. And the unsampled fraction is laid out in the tray, and the other lot is placed in a bag. Another way they do it is they use a tablespoon. They use the back of the spoon to scratch a line down the middle of the core. Everything on one side is put in the bag, and everything on the other side. Not a tablespoon seems to work quite bad, or any kitchen spoon seems to work quite well. But I don't think it's as accurate as using a riffle splitter. But then, of course, we've got the modern technology of scanning the core. Today, I recommend that on advanced projects using both laser inducted breakdown spectroscopy and XRF to scan the core. Remember, this is a scan. You can't do any real, if you're going to do any geological assessment in terms of what the origins are, or genetic paragenetic studies, you're going to have to spend money on whole rock analysis and complete analysis. This will give you ideas, but it will only partly solve your problems. It does help demarcate structures, alteration, and various other things. In fact, for alteration, the spectral scanner, hyperspectral scanner, is absolutely ideal. And again, scanning with hyperspectral scanner is important. But as you can see, the costs of this can be high. I've included the ALS costs here from the current manual catalog, and you can see they are quite high. If you're drilling it at $700-800 a meter, and you're adding another $40 to $50 a meter analysis plus your assay. You remember your lab assay is still going to be paid for at a 29. You're now pushing up an extra 10, 15, 20%, and there's QA/QC at 20% of your costs. This all adds up to making assay expensive. So these scanning devices are helpful, but they can add to costs, and you want to make sure you absolutely need them, and only the portions of the ore body that you need to know something about are scanned. Also, it often means it also requires bringing the equipment to site. In many countries, that's not that easy. So there are issues involved with doing it this way. These things are often designed for countries like Canada, where it's very easy to do these kind of things, and not in Africa. So what I try and do is sustain the chain of custody and make sure that everything that happens to the rig is of the same quality all the way through the process, right the way through to chemical analysis. So you've got field rigs, photography, checking and measuring, all logging, splitting, sampling. All of that is audited. The whole thing is now on audit. And there your chain of custody goes from rig through some field preparation, through loading the samples, through the lab's operation, and right through to the QA/QC. That is all the ambit that I operate under. The main the brain bit is my aim is to make sure that this quality control on this side is actually as real as it is. And one of the points that Julian was talking about, I've had a lot of business, done a lot of business AMS over the years. But one of the things that one needs to understand when you're doing quality control is that a sample is a sample and it remains an unknown no matter what you do to it, unless you do a check analysis and a duplicate on it. And it's cost a lot of money to do duplicates on all your samples and check everyone in the lab. So there's a percentage, which is about 75% of your samples, which remain unknowns. In other words, you've got to assume that the laboratory did not make a mess on that particular sample or any one of those particular samples. QA/QC, all it does is give you an indication that the assay process is operating correctly. It does not indicate whether all the sample assays are actually correct. In other words, if the operator on one of the instruments misreads on one of your samples, you're never going to know. Now, a lot of geologists don't know that. You are never going to know if the mistake has been made on your samples. If they're making repetitive mistakes, they'll come up in the QA/QC as well. But I've been on projects where I've been suspicious of about 5 or 6 assays between standards. And when we sent them back, lo and behold, they weren't the same. There was a mistake being made. It's just that they were out of sequence. And the big issue is putting in the QA/QC. This is part of the sampling process. Where does it go in? How are they put in? How are they placed in the bags? Now, there are many issues. The laboratory, I've had to deal with a lot of things. One of the things I insist, for instance, with QA/QC is the client does not use QA/QC items in the plastic containers that they come in. This is a 9 or 10 kilogram containers. You use sachets. And then you do not tear the labels off the sachet. Oh, sorry, you do not open the sachet. You do tear the labels off. They're designed to be taken off. My apologies. But you do not open the sachet under any circumstances and place it in the bag. Excuse me, but the lab knows it's the standards. They see the sachet. But they also know it's a standard because it's a pulp. Your sample is not a pulp. They know that's a standard. Doesn't matter what you do, the lab knows that's a standard. That's why you put 3 or 4 different grades of standard in, and the sachet is put into a bag and it stays sealed. It does not get opened under any circumstances whatsoever by you. Only opened by the lab. Because the moment you open it, they'll say, but you contaminated it. And that's the problem. So they do know what a sachet is. But what they do not know is what the blanks are. This is very important. Those blanks, or any blank that you use, should be a material, and I normally recommend that its material is going to be crushed and pulverized the same as your samples. So it's going to pick up contamination in sample prep. And what I normally recommend that people do is they go and locate a granite quarry or a dolomite, silicified dolomite quarry, or a quartzite, something that is totally barren of gold. You take that blank, you send it to the laboratory to test it. Don't send it to 1, you send it to 2 or even 3 labs. And then that is what you use. Now, who crushes it and who pulverizes? Now, to get it to a suitable size is quite difficult. Now, another recommendation we make is use barren core, but you cannot guarantee that all the core in your blank is barren. You're going to need, over a long-term project, you're going to need almost a ton of blank. Another help is to actually ask AMS or any of these people to prepare blanks for you. That can be done. It adds cost. They do a fine job. But my view is that the blank should be prepared and on site in bags. Another way we've done it is we've actually got to garden centers where they have crushed stone, and to concrete quarries where they make concrete, and buy that stone and just use that where the stone has been washed. Again, you assay it. So there are many ways of doing it. All you have to make sure of is 2 things. One is completely blank in what your target element is, and number 2, that it is of a similar size that it has to be crushed. So it follows the same analytical process. And then the issue with duplicates, there are various rules for duplicates, but on those colored little blocks are templates. I'm very loath to use a random number generator in a database to generate QA/QC items. I believe in using a template and then just switch the templates over. There's a reason for that. We tend to find that the algorithm on these things doesn't actually separate adequately the various QA/QC components that one would like. And so one uses ones that and those are just examples. There are hundreds of examples that one can use. And then that's diamond drilling. This is RC drilling. I'm not going to go into details, but in these examples are just classical examples, and one is the way it should be done, and the others 2 ways away are the old way. And my trouble is the old way is still being used. In this particular example on the left, the cyclone is going through the middle of the riffle splitter. Now we use this to get people to understand that the diamond riffle splitter is got a width to it. You have to use all the chutes, not the ones in the middle. I've just audited a laboratory where the riffle splitter was painted. In other words, it was like the yellow one in the middle. But the wear in the riffle splitter is in the middle. So in other words, for every sample that's gone through that riffle splitter in the last 3 to 5 years has gone through the middle of the splitter. You need a hopper on the splitter to make sure the sample goes through the entire width. And you need to make sure that the coarsest fragment in your sample can get through the splitter. You don't want pieces sitting on the top. Now, the middle diagram shows what's typical around riffle splitters when they split away from the rig. There's a pile of dust or lost sample material around it. That is a problem with riffle splitters. They're dust generating, as are the whole RC process. The process should be designed in such a way that nothing escapes. Once that sample is being taken, you can't lose material. And this is why I'm particularly fond of the device that's on the right, the column splitter. This is, again, another Australian design. Like everything that's good in exploration, and because they so, and I'm going to use the word anal about everything, Australians do a fine job about inventing things. But my remit's got bigger. Because of my fascination with weighing and sampling and matching things up, people who were sampling are trying to relate the grade on the haulers out of the pit and the weight. So I had to assess the weighbridge. I then had to assess what was on the back of these vehicles and discovered they were overfull. So they were losing material, like sample, they were losing material along the way. Now, that affects the weight of the vehicle and the amount of ore taken out of the mine. And so you've got to make sure that these vehicles are loaded properly. Ore blending. How do you sample a blending process? It was a difficult process, but we worked ways out. Another place was copper flotation, sulfide concentrates. The guys are taking a grab sample out there. Was it suitable? Yes, it was. Material so homogeneous you can take a sample anywhere. But we tested it. Yeah, they're sampling with a shovel. This is a heap leach washing plant. So they were doing head grade with a spade. You can't do that. That's not going to give you head grade. We've already discussed this one in the middle. But the question often comes in, how do you sample heap leach? A heap. You need to know what's in that, what the grade of that heap is. Well, there are various ways of doing it. You can auger, there are various ways of doing this, and it's done, it has been done. But a short case history, we're going to look at, this is a case history we sampled to do a column test. In other words, we're going to do, this is now in the laboratory to see if the extraction process that was being used was correct. So I went to my old friend Petard and see how we could help him. So I decided to test it. So I asked the operation in the field to bring to Johannesburg 600 kilograms of ore, which they duly did. Took it to Johannesburg. And the place where we were going to do this test, the laboratory had a large concrete slab, which I was very thankful for, at the back to where we could do this experiment. It allowed me to test these processes, which are theoretically outlined in Petard. So we decided to divide that 6,000 kg heap into 3 heaps. Now, this was done by using a prime number of diggers. We used large shovels. They were the same shovels as they used to shovel coal, and they were big. They were healthy, strong men, and we made it a bit competitive. There's a bit incentive, but they had to work exactly the same. So they had a coach, which is myself. So what we did was, the reason we used a prime number is it was an odd number, so that the first guy did not put his second load onto the first heap in a regular fashion. So Digger number 1, put on number 1. Digger number 2, put it on number 2. Digger number 3, put it on number 3. Then digger number 4, put it onto number 1, 5, 6. Then number 7, put it on number 1. Then number 1, put it on number 2. So that's how we load. So we've got as random as possible loading of the heap for 2,000 kilograms. And then we use them for 3 different processes. People think I'm pedantic. I try not to be, but I want things to see if they work properly. And when things are in theory. So what we were going to do is we're going to use a column. On the left is a 256 kilogram ore column. They came in PVC pipes of 2 to 3 or 4, 6 meters, and the material was placed in the column, and the solutions to extract the ore were passed down the column. And I came out the bottom into that container, which is a pregnant solution. So it's trying to emulate the heap process you see over on the left. So the other two was what I wanted to see is, could I get a decent head grade first, and what it was, so we could actually get a really accurate site. And I wanted to test the various slab gates approaches. So the 2-dimensional slab gate is to take the entire 2,000 kilogram heap and flatten it to a certain height. I think we flattened it to about 3/4 or half a meter in thickness, rolled it out and took a grid of samples. In fact, diagram shows a 25, but in fact we took 100 samples. It was a 10 by 10 meter grid. This is a 1-dimensional slab gate. It was like a long snake of the ore, and then we sampled across it. And we took the entire sample, it was a channel sample, and then we took 42 by 0.5 millimeter samples. And lo and behold, we got I would regard the most perfect head grade I could ever think of. But not only that, both slab cakes on this particular exercise were within 0.2% of the particular ore we were concentrating. So then, with that kind of knowledge and background from the past, today I go onto sites and I not only help the geologists, but I look and see as a sort of dispassionate observer how things are doing. And here is a mine that's operating as perfectly as you possibly can. And the chuck you see on the hauler on the top left is correctly loaded. It's not overloaded. And it's okay to lose material when you're tipping. That's not going to be helped because that's in a confined area. And there it was, all the sampling on the belts and everything is completely in place. So this is to a stockpile, all is in order. And not only that, they were using the portable XRF correctly. And it was being bolstered by continual laboratory assay. And it was an amazing exercise. So my concluding comments are, sample must represent the ore body or the medium being sampled. It must be representative, therefore, and it must be homogeneous, as much as homogeneous as possible by the time it arrives at the lab. Sampling should always be supervised by a suitably experienced, competent person at all times. On our gold mines, the underground sampler was not the most educated person around. Sadly, it's a repetitive, boring job, but it's got to be done by somebody who's prepared to do it. And without being sexist in any way, my experience around the world has been that women supervisors are the ideal for this job because they are insistent that the job gets done properly. They're highly competent and they do the job perfectly in all respects. And I've seen it in Australian mines where they have been using many of the samples of women. Sample material must not be lost at any stage during the process. This is critical. You've got to start with the material you start with is that material that you're going to end with. Whatever falls out of it along the way must be kept to it. It's not possible to stop all losses, but keep it to the absolute minimum, and that minimum is consistent across the entire process. And everything must be done is consistent and repeatable, not only the managing sample loss, the whole process. You suddenly change the way you're sampling on a rig in the middle of a program. It must be documented. It's time, date, and everything done. And then there is statistical programs you put in place with the data. You see that the data before the change and after the change matches. If not, you've got to start looking at correction factors. You've got to make sure that all sample management is correct. So that, in other words, your sample leaves the rig and moves along the entire process. The insertion of quality control materials, it's managed by someone and signed off by someone at all the times. The sample security is great. I've been on projects where samples, I have suspected samples are being tampered with for whatever reason, and often criminally, you have to ensure that that sample security is perfect. I was involved in a project about 10 years ago where we were dealing with an old-fashioned mine surveyor who'd been given a job on an operation, and his authority was, he felt his authority had been lost that he'd had in previous years where it had been. The situation had changed.
Hi, Keith, you have about 5 minutes, just to let you know.
I've got 2 lines to go.
No
I have
worries.
2 lines.
No worries. Sure, thank you.
So sample protection and sample security are the main issues. And then the database, we will get, that's a whole nother talk. It has to be robust and accessible to only those who need to use it. Thank you very much. Thank you for listening. I'm sorry about my voice, and I'm sorry I don't think I was quite as clear as I'd like to be, because it's been very difficult speaking. Thank you. Are there any questions?
Keith, can you hear me? It's Matt here.
Yes, Matt.
Hey, thanks for an excellent talk, an excellent reminder of the importance of the basic data underpinning the resource estimation process, which underpins everything we do in many respects. I really enjoyed it. The last comment that you made, I found particularly pertinent on the database, because I think that's an area that we perhaps are neglecting to a certain extent. Do you have any comments on that? Have you had a good look at them around the traps as you go?
My relationships with databases and database systems has been a pretty hairy one. I was around in Australia at the time Acquire was being developed, and when Anglo Gold took over what ultimately became Anglo Gold Australia, they actually, the person that worked for us at the stage, the database manager, was actually the guy that developed Datashed. And I've looked at these various databases over the years, and my problem with them is that there is one fundamental issue, and that is the management of quality control. They do it beautifully, I'm not arguing about that, but what happens in the system, and this is where I believe, again, this auditing process comes in, is that you go along and say, when did you have the quality control corrected, or how have you had it corrected, and they haven't had it done. In other words, they know there's something wrong with it. They've got a bias between check samples, or there are odd spikes in CRMs. They just ignored them. They just recorded them. There's a spike in the CRM. There should be a protocol in place related to the database of exactly how to manage what's in the database, so that what comes out of it actually reflects all the quality control work you put in. That's one issue that I have with it.
And that's a good one. I've come across that as well, that people record the issues but have no management system in place to fix it or correct it. Yeah.
Yes. How do you correct it? Now, Matt, I'm in the process of writing a book, which I'm actually not going to write until I get a team of people, and it's going to be an edited book rather, which is our South African instruction manual of how to do all of this. And people like yourself and many other people we should start putting this together. And one of the issues is we need the database expert to come in and say, this is what should be done, is it? And how we manage it and how things are corrected. The other problem I have is where data is corrected, which data set do you use when
Good one as well.
when you're finally assessing the data, the old data or the new data? Or when you send a set of check samples in on data that you think is wrong and it comes back exactly the same, which data set do you use? Do you use both data sets, or you've got to have a protocol to discard one and others, because the values will never be the same. This is the book I'm thinking of writing, is that every process has some way, may not be based on science, but rather a convention, but that everybody sticks to some kind of convention in handling all this kind of stuff.
Great idea about the book, Keith, fully supported. Thank you.
Yeah, but I'd like to talk to you about this book, because I can't write something like, I don't have enough experience. You know, I've always been on the geological side and the geochemical side, but put a resource component into it, to put the whole, so that this book can be sold. Australians have got something similar, but I don't think it covers what I have in mind. Everything. It's a big, thick manual that's saleable through the GSSA or whatever, where people like yourself and I, who are now going to march off this mortal coil in a couple of years' time, hopefully later than sooner. Put down this experience that we've had over the years. I don't know when you came into the system, but when I came into the system, it was actually a dog's breakfast for sampling and data collection. The labs at Nokia OQC, labs like Anglo American research laboratories thought they knew it all but didn't. The data that are now old, I would argue that the old resource data going up to, I would guess, possibly 1980 backwards is just fictitious. I don't think it's accurate at all.
Yeah,
that's my view.
Okay, thank you.
Okay.
Yeah, I like the book idea. Matt and Keith, looking forward to that one. And Tanya's here also, so she'll get it in the GSSA bookshelf soon.
Yeah.
Thanks so much, Keith. Great presentation, very insightful, all your experience.
Thank you very much.
We
Thanks for
appreciate
listening.
the effort you put in and all the photos that you've collected through the years. I mean, it's eye-opening for some of us. As you said, most of us here were not even born when you started working. So it's good that we get an insight into that journey that you've taken. Thank you so much. Any questions for Keith?
Yes, I have a question. Keith, you know, we speak about the different sampling errors that come through in, you know, obviously your process, etc., and, you know, controlling that as much as possible. In your opinion, how much sort of error do you think analysis contributes? And let me just explain what I mean. So I'm talking specifically PGM. I know a lot of your examples, sort of gold and copper, etc., but, you know, on the PGM side, when we do analysis, there are different methods we can use to do assay analysis. And we do see differences between results from these two methods, you know, the fire assay versus the nickel sulfide. You know, how, I'm just trying to understand what maybe a good way would be to get around that. I mean, would the best place to sort of deal with that be in your mine call factor, or, you know, at an earlier stage?
I'm glad you asked that question. If you go into Petard, he takes that area equation and he tries to assign a percentage contribution of each component of the area, or right across the entire process. The preparation and assay component, they assess only, he gives a figure of 4%. In other words, the smallest component. I take it and I assume that he's thinking that, well, that's as if the assay is perfect. My problem is the assays are not perfect. And I do not believe that over the totality of the project is just 4%. I think it's a lot higher. And that is why it requires such vigorous and rigorous attention to the whole process. Way I do these things, do you guys have data where you've taken a series? You need you need a range of samples across all your ore types, a big sample, which crushed and homogenized as a big sample. So you've got a large portion. And then what you do, you assay that sample by both techniques, each of those samples by both techniques a couple of times, 10, 15, 20 times, and see what your range of assay is on both techniques, and then look at the two together. And what you can do is, if you've got a really big data set and it's consistent enough, you can develop a factor to correct from one assay to the other.
Okay.
Is that what you have in mind?
Yeah, I mean, we've had a look at that, and unfortunately, I mean, obviously we've done the testing. Unfortunately, the range of, you know, difference between the two methods we see is not consistent. So it's not consistent enough that we feel comfortable to use a factor. And I think, you know, that's why a lot of it gets absorbed in the mine call factor itself.
Yeah, I see what you're getting at.
Because even the labs are, you know, even the processing department are using different methods at different parts of their sampling. So it becomes a tricky one.
You see what you've got a problem of apples and pears. There, two different processes intermixed with each other. And there are lots of factors involved there. First of all, what the nature of the ore itself will affect the assay. So certain ores will affect fire assay by lead extraction, and less away than they will nickel extraction and vice versa. So that's why you're going to do it across the whole range of ores, test it, and see if it's still unpredictable and there's something wrong with the assay technique. Because similar ore should behave exactly the same way over and over and over again with this assay.
Okay. Yeah, I mean, that makes sense. But as you say, I mean, I don't necessarily believe that it's only 4% that gets
not
introduced. It's definitely,
No.
as you say, you put in QAQC programs, but it's sort of a drop in the ocean. You can't assess, what has happened to the remainder of your samples.
But you see, the other issue is when you've got different processes across the mining operation, you've got the way the geology, and this is, I've seen it. I've been, and when the Amandelbult robot lab was put in, I went there and saw it being done. I was quite interested to see this thing and how, I don't know if it's still operating. But remember, the various processes of assay are messy, and that is the problem with them. They are, I don't know how many people know, but it's actually one of the oldest means of chemical analysis in the world. It was actually developed by a Stone Age, the way a fire assay is done was developed by people in the Bronze Age. So it's old, and the modern technique, the only improvements has ever been made, in my view, forget about the management of it, I'm talking about the actual technique, is the addition of modern analytical equipment, the ICP spectrometers and optical emission
Microscopes, yeah.
So those things have improved it, but the assay technique is messy, and I don't know if you guys have spoken to CSIRO about developing the X-ray photon technique for platinum.
I know there is some technology in terms of scanning, etc. I know that in our US operation that they do use something like that. But I mean, they're expensive, and it's specialist equipment, and I suppose when you have large operations, it may not be practical to have that everywhere. That's also the challenge. But there is definitely something that's that is in the market.
The important thing is just remember, on a mine, when it comes to grade control, it's a daily function, therefore has to be done. That's why mine labs have always existed, and if you can bring a commercial lab in to do that job for you, in an off the property, but doesn't interfere with the turnaround time. You've got to make sure that your turnaround time is within the requirements of the mine. That's the first thing you have to do. So when we brought in outside labs in Anglo Gold, it was possible to do it because and it can be done in South Africa, because those and with the platinum, because those mines are all near major centers. So that the sampling process is done by one group of people doing the assays. Now, what we found was that the sampling methods and the view of the way things are done by metallurgists versus geologists is often quite different. And again, by the survey teams and by guys doing the exploration of the mine, and you've got to unify these things and that's what I do. I try and unify them to make sure. I sit down and ask them, what do you do? How do you do it? Show me what you do. We'll go through the entire process. It takes 2 or 3 days with each group. And then you try and match it. Now, I found on one operation in the Congo, the problem was that metallurgists were not, labeling these samples correctly. So a lot of the samples were mislabeled. And B, when they brought them into the lab, they hadn't been sealed. They just threw them down. The material was wet. It was essentially a grab sample versus an organized sample taken by the geologists and the grade control people. They were all working differently. But so when they did reconciliation, we couldn't work with the metallurgical samples. Everybody must be taking the sample in a way that matches what everyone else is doing. And that's also quite important.
Okay.
And that is a major issue, to get the sampling to match.
Yeah. No, 100%. That's definitely a challenge.
Yeah, and really it is. It's a serious challenge. And that's what I based my work on, is the fact that things don't match. And this, in one place, the sampling is adequate because the way it's being done or because of the environment. Often it's not often a people problem, it's an environment problem. So you look at different ways. I mean, the underground sampling, to try and control it better, we used saws, and that worked. But they can't be put in everywhere because the miner won't let you use his water and he's compressed air, so the saw won't work.
Yeah.
You know, so it's things like that. It's got to be a team effort. So senior mine management has to be on board. If they're not on board, it's not going to work.
100%. No, thanks very much, Keith. Appreciate your input.
It's wonderful to be back with the Geological Society and see what's happened in between. But that is not my subject now. Sampling data management is a very vast subject. And I'm very happy to have had the people that have spoken before me, because they've explained a lot of things and the reasons why our methodology came to be. And it will help me not to talk too long. So I'm starting with some of my definitions, how I see things, the business context for geology, critical success factors, then the main theme of the talk, which is the sample data life cycle. And Keith, really, it was a wonderful background to that. The solution context, which is on the software side, the methodology and the benefits. So sampling, I want to define it for here for today as a selection or a subset of the population of interest. It must be representative for estimation within confidence limits. I'm pointing you there to, we need precision and accuracy, otherwise we don't have confidence. And it has to have a spatial context because we are dealing with geology. Data management, I've often been told that Sable is really a SAP for geology. So I went to SAP on Google, and yes, I've used some of their definitions. They are saying on its own, data is useless. You need an effective strategy, governance, and data management model. I couldn't agree more. It's a plan of attack. They say data management is a plan of attack as a set of procedures and practices to ensure that data is secure, available, and accurate. It is not just a database. Rigor, and I think this, I was trying to, why have I got it in the talk? But Keith has explained it all. Not only that, on a lot of the talks we've had have explained this thing. We are in the context of evaluating, and we in the sciences. So we need to be strict, thorough, and careful. A lot of our data is qualitative. Today is really mainly quantitative, but still, we need that rigor, scientific rigor. A lot of what we're doing is actually research, even though we're calling it exploration or something. Then classification. I've spent most of my life building good classification systems for our clients and for the geoscientific data that they require. It's an arrangement of things. We need to record geoscientific observations. And it's an action or a process. It must support business procedures. Now, I just put this in yesterday because there was some debate on, quantity data and how much data and what data. So it's all very well, if we're talking about we need reliable data and we need data management, we need all these things. But what is it? Well, what data do we need and why? And what is making it easier for us now? And I want to put us in the context of the mineral reporting codes. The first one, they started in 1994 in Denver, which is after Sable started. But we were all in South Africa, doing things very professionally, and we had to, as Keith has shown you, explain why we weren't getting things, and we bumped into the directors in the lift, you know, that were giving us these millions to be drilling these very long boreholes and things that we were doing. And they would actually ask us, you know, how's it going? What's happening? So we had to be very careful. Money wasn't just the easy thing that you're seeing today coming through the stock exchange and so on. So data quality. So, okay, it's all about confidence estimation. So we need all of these samples that we're gathering are really just estimates. And I remember when Prof. Dick came to one of our early conferences, disabled user conferences, and that's what he said. He said, you know, it's just an estimate. You know, he also, you know, made us realize, but it's, you've got to represent it properly, otherwise this estimate is going to do nothing. So, okay, your estimate then, if you want to build confidence, you're going to have data quality, otherwise you're not going to be confident, and you're also not going to get to knowledge because you'll have wrong information. The quantity of data it's not really up for debate. It is how much do you need to build confidence? So where I grew up in Anglovaal, you know, I was very privileged. We used André Janel, he was under Matharon there in Fontainebleau, so the French were leading geostats, and then Dani Krieger was also on the staff, and often he would just ask me to write a program for him because they didn't have, you know, the IT people were all commercial people. So I got exposed to this variability and heterogeneity and all these things at a very early age. So that affects the distribution of the data. So a lot of what people have talked about is, you know, how much data do you need? Well, that will depend on your ore body, on how you're sampling, on what you're sampling, on these sort of things, how on the beneficiation, how the ore is going to get out. And the data distribution will also depend often on the geostats, because we are spatial. That's why geostats came to pass in my lifetime. So, and we've all been building on the shoulders of the people that came before us. And I think that is a message that I must also pass to the young people of today. Because if you're wondering why we're doing what we're doing, or yeah, we were being guided by the people that were the leaders of the day. And I think if you can carry on building on the shoulders of those that come before you, you're going to get somewhere. Otherwise, you're going to go back to square one again. So when you start at exploration level, which are the juniors, and I agree with Keith. I mean, I think anything's possible there. And I think, you know, often they get away with murder, but that, you know, they don't want to be spending money, and they just want to get something and float it on the stock exchange, and then people must invest. So it's quite a dangerous area. But as you come down from exploration and you want to declare now an inferred resource, you need more confidence. So you need more data quantity. You're going to need better quality and distribution. And if you want to then go to indicated and down to measure, where we're trying to get to if we want to mine, your confidence must be better and better. And so you're going to, that dictates what data you need. But yeah, what happened in my life, well, I think it was between the first SAMREC and the second, but people can correct me, is that it had to be mineable. So maybe at exploration, you can still get away with declaring something in situ, but the minute you want to go and come down here, you're going to have to take the modifying factors into account. And the modifying factors could very easily be this data that people think is not being used. But they are the sort of socio-political, environmental, safety, legal, can you beneficiate it? Are you going to have water? All these kind of things. So a lot of the data that's being collected in our databases is there to hedge the future, because sometimes there isn't a way of beneficiating that ore now, but in the future there will be. I mean, you can see what Anglo Platinum's done and other companies over time in how maybe there will be other techniques coming available. So you want the data in the database, and you're spending so much on all the drilling and the exploration that actually the way that we were brought up was, you must better get as much data out of this as you can, because we've spent so much money. We can't be doing this again. And I don't think that we will ever be doing those huge drilling campaigns again. So if your modifying factors are successful, then you're going to jump this gap from indicated to probable and measured to proved. So you also need to be hedging the future. And really, I've described also the business context now of this data management. So I always saw data management as part of the business process. It was never something that should have been a bolt-on activity or a database somewhere over there in the sky and a data capture clerk must feed it. No, from the beginning, we said the geologist must log into this thing. This is a logging tool. And that's why it was called Standardized Approach to Borehole Logging for Exploration. That's where the name Sable came from. So the GSSA was also very instrumental there. We had a poster in 1984 in Potch at the Geo Congress, and that's where the other mining houses approached Anglovaal, and they said, look, it was Anglo American Prospecting Services, GenCore, JCI, Goldfields, and was there another? I can't remember. And they said, please, can you make this thing available that you've got shown on this poster? And there began a whole journey. But okay, I think let's not go there. But the business context then is that we have complexity and we have to deal with it. And what we're sampling, and as Keith has just said at the end now, it's very difficult to reproduce a sample. But why do we go to the extent we go to get the geology down in detail in the way we do, is because geology is complex and we want to understand all the different processes involved, all forming, structural, alteration, whatever. We want to understand these things, so we need to know where things are changing, and we need to get our standardized terms, and Alan referenced this. So every code that we use must be explained, and it must also reference, if possible, and I mean, it should, we were even doing this in the 80s, so it is possible. We don't have to make up our own codes. I mean, we used to use USGS and the British and our geological dictionaries in those days. So there's always been explanations of codes that the whole world will understand, so that when geologists come in here, from wherever they're coming from, they will understand. So now, when auditors, so what I'm saying here, if you want data to be reliable, it must be understood, must be easy to understand and verify. So you need that transparency of what is this code and what does it actually mean. I can go and look it up in the dictionary. It must be simple, easy to combine things, because we're dealing with qualitative data often on the geology side. So sorry, I've gone off into geology, but we need to know, if we want our sample to be representative, then we need to know what it's representing. So we need to understand the geology. We can't just go sampling around. We also then need data independence. This is a principle of software engineering, and it says that you don't, the application here is don't log for the model. Don't take on capture data just for a particular application. Your data must stand on its own, with its own meanings, and it must stand the test of time. So it must be sustainable. So fortunately, we've always had that. We in the 80s, even, we were already feeding all these other systems, modeling systems, and Sable was often used as the offline capture for these other systems by the different mining houses. So what you see must be what you get. So the capture must actually keep your head in the geology, help you to understand and classify it properly according to these terms, and it will hold you through training, through different people. It must stick to those, what Alan called the standard operating procedures, which are the work practices in the different mines. And yes, I mean, you can't have your capturing one way and then you must pull it out, or the database is some other way. It must be simple so that geologists it can become a tool for geologists. And then you get this transparency, because in the previous slide where I showed, if we want to turn something into resource into reserve, from a resource to a reserve, we need to jump from, we need the primary data for the auditability and to understand the complexity, but we need to simplify it to discrete units, because those are the zones often that are going to be modeled, that are going to come across in a model. And this can sometimes is based on stratigraphy, sometimes it can be based on anything, but you need to try different things to get across there. And the auditors must be able to see how you made the decision, why, and is there a better way, and do they agree with it? Forgot to set my timer. Where am I, Tsecho? How long have I spoken for? Are you there? No, he's not there. Okay. Critical success factors. We have is a predefined sampling protocol, and I'm so happy that all these people before me here can stand on their shoulders because they have described why we need it.
You still have some time, 20 to 25 minutes. 30
okay,
minutes.
Thank you, because I've still got quite a bit to say. Okay. Can you tell me when I'm halfway? So, all right. Predefined, you have to have a predefined sampling protocol, because why? It's very simple. You need to know what the sample represents. I mean, you've heard that from Prof. Dick. As I said, we were so privileged to have him early on at one of the user conferences already. Sable, and that changed my thinking completely. I thought, well, this thing is very simple, you know. So if possible, you sample geologically. That's it. That's what we're doing. Then second thing is, if the subject is sampling data management now, we need to track the sample through the data life cycle with a sign off at each step. And I think the things that Keith has said this morning are foundational to this approach. Then for me, you know, we are in the world of software engineering here, and there have been principles ever since I was born on a mainframe. And they won't change because they are fundamental. And the one is that an application must be a tool in the hands of a user. I mean, if you want a successful application, of course. The tool must then not become the job. So where we see apps become a bolt-on activity, or solutions being bought and then they become unused, or people hate them, or all the things that go on out there, it's because it's not actually helping the geologists to do their job better, and it's not helping them to enjoy their job. So the fundamental here is the user must be the master and the computer the slave. Now, that is how I was trained at university. Some of these fundamentals have gotten lost in business, where actually it's gone the other way around. You know, there's almost a control coming from applications, and they don't even care how much pain they're causing the users. They must just do it that way. Well, that is completely wrong, and you must fight it. Critical success factors in our context then are accountability, auditability, and transparency. I think if you have accountability, then you have people taking responsibility. After listening to some of the things yesterday, I just brought in that little hourglass there, or timer, because I've realized that, you know, and people like Keith and Prof. Dick and some other people that have spoken, we are older, and I'm sure you're going to hear Matt just now as well. We have perspective now. And I think often the young people coming in today are just hitting all these problems. And I mean, because a lot of what I've heard here has been exactly the problems that we were solving in the 80s are still being cited as problems today. And yes, data management has always been a problem. I've got a big fat textbook here called Modern Database Management, and I bought it in 1980. So, yeah, you know, we must with the perspective now, look at what works and what has worked through time and build on that, and not take the whole world back to square one again, if possible, in terms of these applications and data, because it wastes a lot of money and takes geologists time off concentrating on their job. So really, this is probably the subject of my talk now, is the sample data life cycle. And I'm so happy for Keith's and the Amos talk before. But yeah, how we've come to see this is the database is central to every single thing, because in the world of Sable, it provides governance. So it holds metadata that's got rules and definitions and conventions and things in it. So we need it to be there. And we need everything you do to be able to access it. So I'm going to start here and say, if you could start with a sampling instruction, actually created from the database, and first prize, if you could create it from your reserve model. So even where, I mean, Keith showed us some examples where you got blast holes and stuff like that. You know what the reserve model is, otherwise you wouldn't be mining. So you can already say, well, we're expecting these samples because we know we want you to sample every so many meters. And even if you're putting a geophysical instrument down your blast hole, you know what geology you were expecting because it's in your model. So now you can verify against that. So if you can start with a sampling instruction issued from the database to the field before they actually sample, that's fantastic. Now, if you think it's sounding far-fetched, it shouldn't be, because you should have logged it geologically. I mean, I'm not talking about blast holes now, but you've got your reserve model and things like that, and underground you've also got a model. But if we're talking about drill hole core and so on, you should have logged it geologically first, because you have to understand the sample must be representative. So now you shouldn't be sampling if you don't have an understanding of the geology and how to sample it, and you don't have a sampling protocol. So if you stand on the shoulders of the guys that came before you and put in all of these experiences they've had, so that you know how you're supposed to be sampling. Are you supposed to be sampling to a contact? Are you supposed to be sampling across the contact? Are you supposed to be, well, however, there's many ways, and for different commodities and different styles of mineralization, these are all valid. But you just have to know how you must do it. So you've now created a sampling instruction, and there I'm introducing the concept of a sample name. I personally prefer a sample name. Yes, it must be unique, and it's very nice if it can be created off the database from the relational data in the database. Because our samples are spatial, it's good if you've got a reference to the location. So either the borehole ID and the deflection, if there are deflections, the working place, the block, whatever, the face name, whatever. So if that sample name can have some relational data in that you can see and understand, then you will at least be in a situation where if it falls off the back of the truck on the way to the sample shed, you know where it came from. And the database then, because you've logged the geology first or have a model or whatever, can actually create this instruction. The spatial reference then means you've got a location. You're not just dependent on an XYZ coordinate, which of course, if you're doing grab sampling, I mean, that is what you're going to do. But even there, you know, GPSs are very powerful. You'll know exactly where it is. The spatial reference will also say, well, from where to where. So if you're using what we've used over the years, is everything is linked to a profile, a physical profile in space, which has a collar, and then use it is the distance from the collar. I also believe, you know, you cannot depend on, you must have froms and tos, and not just two, because the thing you could make a mistake and then you don't know which one it is. So there are various ways of making sure that this thing is valid. But okay, so in the field then, you're doing your sampling according to protocol. If possible, you had an instruction issued from the database. And then this becomes, there's your sampling protocol. And then this becomes a field batch, which is batched when somebody says, yes, this is correct. Now put it on the bakkie and send it to the sample shed or the core yard or wherever it is. These things could be right next door to each other. They don't have to be far, but they could be quite far. I mean, they could be at the rig if you on a dune drilling, or they could be or in the pit, but it could be a way away. Okay, so at the sample shed then, these field batches come in, and they can then be, if you had a sampling instruction, you can simply scan those ticket IDs because, or sorry, the sample name, because it was created from the database. If not, you can then scan them in and they can then become part of the database. But we'd rather go the other way if possible. We don't want to lose control. And it is possible. These things are being done in big operations and working well. Okay, so at the sample shed then, we have field QC protocols, and there's been a lot of reference to that today as to what, and I heard talks yesterday, as to what percentages should be used, how many of this, how many of that, and so on. So we find these are not predictable, and it's very dependent on the place, the culture of the organization, the place. And it's good if you can actually get an auditor or someone else's shoulder to stand on and let him tell you, but I can only sign this off if you do this and this, because I need proper quality assurance here. So what we do is these things are configurable, as the whole of Sable is, because everybody's working slightly differently, but you're doing the same kind of stuff. So you need to be able to say what percentage. So often we find in production maybe 5% controls, and then what sort of controls are you going to do? Is it going to be blanks? Standards CRMs can also be blanks. Some people make their own. I mean, I've seen wonderful plans made where I think Impala is actually doing this. They've got waste. They've analyzed the waste for so long that they know they absolutely can prove that it's got no mineralization in it. So they can just take that and use that as a blank. And then the lab can't really see it. So, you know, there's plans you can make if you've got a lot of data already that you can use. And we've had wonderful explanations of these control samples. So we want you to then have a plan. I agree with Keith, you know, you can put them in randomized, or our protocols, you can say I want it randomly inserted, or I want it every so often and a certain percentage. But before it is dispatched, the competent person for that process must sign it off, because there is the ability to move these controls up and down. Because you may say, for instance, in gold, we want this particular low grade CRM to follow where we expecting where a particular mineralized zone, whatever. So the geologist must be able to change the position of the control. You cannot just computerize and automate it. So that will then go back into the database. The database can be anywhere, but obviously you have to have communications to it. And over time, you know, we've had to make all those plans of having the database on your machine, and then when you get back to a place at night to the office, you can merge it into the other database. We've had wide area networks set up in the core yards at mines and so on, big exploration projects. so that people can log straight in. But we believe as well, as I heard in that Bentley talk, that you must have the logging standard at the front. So these controls must be in place when things are done. Data management must be part of your process. It's not something else. So having done all of these things, then you will get batches then dispatched. And that's also part of the QC protocol. It must be dispatched to 60 samples at a time, must be dispatched, whatever. You've got all sorts of rules, and you can build, that's also part of the QC protocol, the field protocol. So having been signed off, batches are then dispatched. Now the dispatch, I mean, this lab can be right next to the core shed, by the way, or it can be, have to travel quite a distance. But you can have sample registration now of your dispatch sheets, because now the thing that has to be introduced is the blind ticket ID. So you had a sample name, it's in the database. Either it was scanned or it was on the instruction sheet, and now you've got a blind ticket ID. And that can be created as a globally unique ID or some other way, or it can be some incremental with the prefix and some increment. But what's important here is that those samples that go to the lab, nobody must be able to see where they came from, if possible. I mean, mustn't be, this is a reef sample and this is not a reef sample. As Keith said, you know, I mean, what we know is they can also look at the colors of ores and so on. But yeah, we need blind ticket IDs. We also want them, we want to instruct them on this sample registration that we want analyses to be done in a certain order, because we're trying to control what gets done after the other one. And you've got to check up on the lab, because you know, that they're not putting all the control samples on one pile and all the others on another pile, and handling them differently. So it must go through in the process. So together with the dispatch batches then comes the analysis request form, or the analysis requests, that for each sample that's registered with its blind ticket ID, you want to tell the lab what are the different analytes and what are the methods that you're requesting, so that you can request more than one method if necessary, or whatever. Anyway, and we're finding more and more we've had to go to a per result approach. We can't just be a per sample. So for every sample and every analysis, we got to tell the lab, I mean, every analyte, we've got to tell him what method it is and so on. Okay, now that having happened, and it can happen digitally these days, as I say, but it's also good to have a piece of paper that goes with the batches, so that if something goes wrong, there it is. And it's also after sign off. Someone has to sign that off. Then off it goes, or it can be a trigger in the database or whatever. Then the laboratory does its job. It produces lab batches, which can be 20 samples. So your dispatch batches that you've sent can now turn into lab batches. And Keith referenced a bit of this, where, you know, the aliquots, you can only fit so many in, or sometimes, yeah, particular machines. It depends on what methods you're using. The lab then has its own protocols, its own QC protocols, and that was in the talk this morning. So they will be using their own controls. And yes, our control samples will also be a part of that. So the lab will then process its batches, and we want them to actually report, if possible, by our field batches, but it doesn't matter, or our dispatch batches, but it doesn't matter. Actually, we want them to report both. We want to know what their Q control samples were and the order that they did the analyses, because then we can also look at time factors and so on, and what happened on a Friday afternoon, whatever it is, because strange things do happen. So those reports then will come through with a blind ticket ID. Nowadays they can come digitally, but we would like a PDF as well to store in the database for the auditors. They will come through by field and lab batches. And I'm so glad Keith talked about this. But yes, they will be loaded into an area of the database that we call clearing tables. We actually call it the ETL area, extract, transform, and load.
About 10 minutes.
Okay, thank you. So it's loaded into its own area, and there we run our own QC routines, which auditors over time have told us, we want this, we want this, we want this from our clients. And so we did it. So over time, and Sable then produces the queries itself for whatever batches. So we QC by batch for the info that we have. And before any of that data gets loaded up, you don't need to know which version you're going to use. Well, you will leave those versions or submissions, but before any further thing, that thing must be signed off. Oopsie, sorry. It must be signed off, because if it fails, this process must happen again. You're going to refuse to pay the lab. So if it passes, you're going to load it up into the main primary area where it's available to be used, and put next to the geology so you can verify it graphically and all the things we do as quality assurance before we accept that data as being able to use for reserve and resource. Okay, so the context really of this solution that I'm proposing is data integrity. It is a tall order, but it is essential for geoscientific data, because if you want it to be reliable and used, I mean, that's the only way to go. And the benefits then would be consistency. Professional data standards are required to transfer geoscientific knowledge. We're not going to get a knowledge transfer through that hourglass from the one generation to the other, from the one project phase to another, from the one company that buys the other. We're not going to get that to happen unless we have this consistency, and probably people doing the same thing for many years because they're working on proper standards. It's going to give us quality assurance, software applications. The software application will promote and support international geoscientific data standards. Why? Because you build it in, and you build on the shoulders of those before. And accountability. Professional accountability is ensured through configurable user security. So this is just a computer aspect where we have strong security so that people can't by mistake be in other people's data and all the things that go on, and fraud and so on. Again, it does happen. We've all seen it. So yeah, just to say, seeing that I have a bit of time, actually we started even before that, but I think this is JCI Randfontein Estates. It could even be Western Areas. But that's how people were working. And so now this is Sable 2, actually. This is after the Potch Congress. And apparently someone else, which was actually Bruce Walters, that drew this. I don't know if anybody remembers him. Apparently I arrived in the field. That is a DOS PCXT that I was carrying. And yeah, I said, look, now this is how you're going to log. Well, the geologist said, well, we're not typists. We don't want to type. And I went through all sorts of shenanigans there just to get that to happen. And yes, we promised them. And I think, Matt, you're here today, but that poster was done in 1986 at the Western Bushveld in Carletonville. There we had that meeting, I think it was in 86. And we did that poster because we said, what is Sable actually doing? Well, we'll absorb the core and we'll give you those logs and things that you've been drawing by hand. But we want the relational data. And so we even had to let them digitize because they didn't want to type. But by the 90s, here we are sitting, and we got to the point where people, so those are just ordinary notebooks. But we got to the point where people didn't even, they refused to log if the computer wasn't working, you know. So, yeah, we had the database was on there, and then those were merged in later. So this methodology developed and matured after 4 decades. So yeah, very mature now. And these are your benefits. It's mature. It's not just a database. It's backed by an experienced team of competent geoscientists and software professionals who've been out there and done the things and seen things happen. They will implement and migrate relevant data sets into an integrated data standard, and that has to be actually set up in a bonfire with everybody involved and standing on the shoulders of those before you. We provide governance and legal compliance required by professional mineral reporting codes and stock exchanges. We've had ongoing product development across 7 generations of the product to supply trusted protocols, ensuring geoscientific data quality assurance across 4 decades. As Ellen referred to the project for which Anglovaal gave me a budget of 100,000 in those days, and it mainly went to the hardware, by the way. It was a Hewlett-Packard Technical Micro. That was 1983. We now integrate all geoscientific data sets required, so we don't have silos already, you know, for quite a long time, required as modifying factors in the mineral resource and reserve reporting. So a lot of geoscientific data sets are required to show that you for those modifying factors, it's not just your basic logging and sampling. And then I just think this is, do you recognize that, Nicole? So I went to a Bushveld GSSA meeting last year in Rustenburg in June. And this young man comes up to me and he says, "Are you the lady that started Sable?" In fact, I think he said that gave us Sable. Anyway, he said, "Thank you for making us such a simple, easy to use system. I've really enjoyed using it." He's a very young man, and I don't know how many generations of geologists after me, but maybe 4, but I haven't sort of calculated it out. Certainly 3 or 4. And to me, that was such, I mean, it made my decade, you know, to see this young man that's gotten of today. And he was one of the big platinum mines. Thank you.
Thank you, Marcia. Thank you so much. It was a nice presentation, very well thought of, and good to see the youngsters as well appreciating Sable.
Wonderful, eh? Yeah. Yeah. Great.
Any questions for Marcia?
Yes, Marcia, it's Keith here. Can you go back to that slide you drilled? It's about the 4th last slide in your talk. About you spent a long time. Could you go back a second? I want to talk about a point Matt brought up earlier, and you spoke about quite a long time as well. Could we go back to that slide? It's it's the one, that one, yes.
Is it that one? Okay.
Yes. We're talking about the data that's come back from the laboratory. This is been my big bugbear for years. I go onto projects and I find data has been accumulating because the corrections haven't been made and because protocols are not in place of how to fix data where the QA/QC is not right. There's no use saying don't pay the lab. This is an ongoing process. They're doing tens of thousands of assays for you, and they're coming in all the time. They're reporting all the time. You've got rigs running. My problem with this is that there is a combination of a lack of understanding of the system by the geologists using them. At this point, they don't understand QA/QC. QA/QC is only going to tell you what's wrong with the QA/QC items. It doesn't tell you what's wrong with the analysis. If one of those samples analysis has been screwed up, you will never know. It stays an unknown. All they are doing is guiding you to see if the lab is performing properly. So to correct these things is a problem. And I have drawn up a set of protocols. For instance, in one batch, you've got one CRM that's out. What do you do? In another batch, you've got 2 consecutive CRMs that are out. What do you do? In another batch, you've got a scattering of CRMs out. Some are right and some are wrong. What do? You can't re-assay every batch. It's expensive. It's time consuming. So what
Yeah.
I've done is I have written for my clients, I write up a specific set of protocols, which are then you people will come along and put into the database. So we can actually put the data residing in the database as effectively, as quickly as possible. So it leaves out segments of batches, not entire batches. So
Yes.
those are returned to be fixed. Now there's another issue here, which often holds up data. And that is the check samples we have at Umpire Laboratory. People
Yeah.
don't put the data into the database until the Umpire Laboratory data comes back. Sometimes that's 4 months hence. So
Yes.
that's not the way I want to see it done. I want the data to reside in the database in situations like that. And where there's a problem with a check sample, say for a batch or for the whole lot, then that data is checked again, and then some plan is made to swap data. In other words, replace it with the updated data, or
Yes.
keep the original data there and replace it with the 1 or 2 assays that have come back and appear to be better. Sometimes this goes on doing 3 or 4 sets of analyses to get certain sets of data right. Often, and I'll give you an example, this new photon assay technique, if there's barium in the sample, you cannot use that assay. But not every sample is barium in. So you've got to then locate those samples and assay them by another technique. So you've got now one technique in the database using a big sample, and now another technique, or should I say a big aliquot to assay, which is the photon technique. And then you've got the conventional fire assay, which uses 25 grams. You've got 2 assays sitting next to each other, where one is using one technique and one is using another technique. And this is where data, because of QA/QC issues, becomes complicated. And have you guys started to deal with these things so they can be handled more efficiently?
You know, I had to stop somewhere with this diagram, but we will
Yes.
very often have a middle database here.
Yes.
We will have what do we call it? It's sort of a middleware database. It will be a stable database, but it's only handling batches of samples. And we can then operate, especially if it's an on-mine lab, we can then reject at the level of a particular sample.
You see, my view is rejecting samples is such that you now got a sample that cannot be used for any process or assessment. And sometimes that requirement is 24 hours. You need to have that data back in 24 hours. This is one of the reasons we shut the mine labs. They were taking 3 weeks to do an assay on underground grain control. You want that in 24 hours. You want that between blasts. So you don't want data hanging in space. You want it to go in, so that, but you still want the QA/QC in place. So,
but I must say, you know, Keith, we do have percentages. I mean, you can have a certain percentage failing. I mean, but we need to be led by you people, by the people.
Yes, no, that's what we're doing. We are being leading you. But my problem is to make sure that the data is usable as soon as possible. So you don't hang it up because the QA/QC on one batch is erroneous. It might not be a problem with the samples themselves. It might be just a standard. So this intermediate database is the bit I rather like. It should be usable. With the caveat is that data for that particular day or that particular time has got data that may be replaced, and therefore you redo the stats or whatever you're doing at a later stage with the data now updated and just see if there's any difference.
Yes.
So in other words, you are having to correct things after the fact sometimes. You can't hang around, particularly where we have problems with metallurgical plants and open pit operations are running a heap leach, and you want a daily turnaround. You want to know what's being taken out of the pit and what's being put on the weighbridge. I mean, I spent hours just on the weighbridge alone trying to work out what is the average weight of a hauler. Because they get covered in mud, their tanks are full of diesel or they've got no diesel in them. They've got huge amounts of oil in the engines. They burn oil like anything. Their tires pick up mud. During the rainy season, they're a lot heavier than they are during the dry season. So it's all this information that goes into the database, which has to be controlled and understood. So the data is immediately usable.
Yeah, I agree. I mean, that's very important, Kit. That's a good point. Thanks so much for the question and the insights as well.
Can I make a observation and a quick question? Firstly, in the mineral resource audits that I do, I'm always very excited to see that the the people are using Sable, because I know immediately that I'm going to get high quality data. It's definitely the gold standard compared to what I can see in terms of poor and reworkable or need to be reworkable data anywhere else. Marsha, a quick question. How do you record in the database, let's call it fuzzy or data that you're not sure of? Is there a way of recording, well, we want this data in the database, but we know that it's not all that great, but we want to keep it there. Do you have a way of recording that?
We do. That, what I'm calling the clearing tables here, or we call it a branch, the whole branch of the database. These things will come in and they'll be called a submission. And for a particular batch that was returned, you can leave those submissions there. And I must say people do. So you can have more than one submission of that batch and decide which one you want to load up for use. You know what I mean? For your reserves and resources. Does that answer your question?
It does, yes, thank you.
Now, the point of this discussion is to try and look at things from a competent person's viewpoint. So we've had the discussion from ongoing data as you're gathering it on operations. But the situation which a lot of people will later face, if you haven't already faced it, is you are now moving on to a new project or a new operation, and there's a whack load of historical data which is there. Now, we've already discussed at length, putting into data sets, data quality, but my point is, well, how does this tie in with our reporting standards and codes, which we need to follow as listed companies? How do you, as a competent person, if you're not already a competent person, you aspire to be a competent person, what are the types of things to look for? And I'm going to try and flesh it out with case examples of things that I've seen during my career. And yes, I will make references to Marsha and Matt and stuff, because as they were talking about standing on the shoulders of giants, they were the giants whose shoulders I'm hopefully standing on. So the whole point is, why do we inherit these old data sets? Now, a lot of the time you think, well, we've got a project, we're going to put it into production and we're going to get it. Well, the reality is that any mining is driven by economics. And again, we've discussed this at length over the last 2 days. But commodity prices and exchange rates fluctuate. So what is a valid project today is not necessarily going to be a valid project tomorrow. So of course, if you're a large corporation or a junior, you run out of cash and you stop, and you've got to either refinance or you walk away from the project and you put it on hold. Technology changes as well. So what we're looking at, we drilled, we walk away, we couldn't process that metal or material at that stage. We just didn't have the technology, or it was too expensive to do. How did geopolitics influence? So, for example, China controlling the vast bulk of upstream processing for lithium and graphite. So what happens when things go wrong and you can't process anymore? What do you do with your project? Laws change. So especially with the growing focus in the ESG. So some things you can do today, you just can't do anymore. The laws change. America is a classic case of that, where the Democrats and Republicans get in. They change the laws every 4 to 8 years, depending who's in power. And then we just overall don't have an economic valid point at that time. When we start flicking it back onto operations, generally the situation is encountered in underground. So obviously Reef Horizons, which you can mine today. Reef Horizons, which you can't mine today, they're not economically valuable. You leave them, mining changes, you go back, mining technology changes, and again, you start going back and having to reevaluate this data that you've historically had. So just a few examples of what I'm trying to describe. So this is the gold price. Now, gold is the one area of exploration and mining where there's always money going into. Even though there's really bad times, there's at least a market for gold. But if you look at the, this is the nominal price, so gold price adjusted for inflation from 1950 onwards, you can see that gold goes through a number of cycles, often sparked by major geopolitical events. So World War I, World War II, this interesting dip here and spike that is 1972 when President Nixon took America off the gold standard. And the US dollar was no longer pegged in terms of the Bretton Woods Accord, but then became what's referred to as a free floating currency or a fiat currency, you started seeing a lot of variability and fluctuation in the gold price, which takes us to 1st of January 1980, when the gold price hit the highest that it's ever been. So in relative terms, even today, we have not actually seen the same gold price that we got back in 1980. Now, again, an interesting thing about gold projects and gold deposits is that, again, in relative terms, you need limited amount of capital to bring a gold project online. You don't necessarily have to have a magnitude of scale. So again, the large South African Witwatersrand gold mines in general in the rest of the world, you tend not to see that. So people will go and mine very small, very high grade gold deposits. You don't need a lot of input. You don't have a lot of operational costs to run these things. So again, gold is a very, very easy thing to do. And as I said, people always want gold. The world's strongest currencies, which are not the British pound or the US dollar, surprisingly enough, are things like the Jordanian rial and the Saudi rial. They are backed by large gold holdings. When we start looking at other commodities, for example, iron ore, again, you can see that there has been variability. It appears to be slightly longer term, again, driven by supply and demand, especially now as we're seeing major changes in urbanization, countries like China and India having massive urbanization drives. Africa itself, if we start looking beyond the borders of South Africa to countries like Nigeria, Egypt, Tunisia, they have, Angola have massive growing populations, and they're going through large urbanization drives. Obviously, to build the infrastructure that is needed, you need steel. So again, we start seeing long-term commodity cycles. But as Matt will tell you, with steel, you need much longer horizons, and you need a lot more infrastructure and capital to make your steel or iron ore project work. That all being said, though, we also at the mercy of exchange rates. Now, in Britain, we are sitting with a very relatively strong pound. It has depreciated by 25% in relative terms to the Australian dollar and the Canadian dollar, but again, it is still relatively strong in terms of world currencies. The rand, on the other hand, looks like this. So as of this morning, the rand was trading at 18 to 1 to the US dollar. So this allows you, because you are now mining a product and paying in rands, but you're selling that product in US dollars, you can actually make a profit. And that's why the large, deep operations in South Africa can continue to operate, because of effectively the arbitrage between the exchange rate. So you can actually make money in rand terms. This also would imply that South Africa should be a destination that everybody's wanting to come to in terms of, well, it's relatively cheap to do business. Unfortunately, there's other factors which influence that perception and risk profile. We also see things like changes in technology influencing the deposits we can and cannot mine. So say, for example, if we go back to the late 18th, early 19th centuries, the type of technology used in manufacturing, or correctly iron ore at that stage, or iron, was what's referred to as the puddling technique, and it could use relatively low-grade iron deposits. So, for example, in Britain and in Europe, France and Germany, they were mining low-grade oolitic iron and iron deposits, which you could process using the puddling technique. Roll on later on to the mid-19th century, where the Bessemer process came in. They could no longer easily or readily process the previous types of iron ore deposits. So what had happened specifically in the United Kingdom was a lot of the iron ore mines in Britain shut down, and iron was sourced from Sweden and Spain for long periods of time. Now, take into account that we had the Second World War coming in, which caused major problems in terms of that. Eventually, though, the Bessemer process was then replaced by the open hearth process, and then we could start processing banded iron formations in the taborites. So again, there's a focus and a move from different types of deposits. And again, as we start looking at this, we have historical data sets, or companies would have looked at, say, for example, banded iron formation, realized they couldn't actually process it with the technology of the day. That data would theoretically have still existed, and someone would then go back and want to use that information or that data in a mineral resource estimate. Now, correctly, we can't really start using that as an example because we're now talking several up to 100 years ago, but that data would potentially exist to at least form the foundations of a geological interpretation, or at least an exploration program that you are going to be looking at. Touching on geopolitics, as you can see, for example, China leads the world in processing and mining of the one thing everybody is very much aware of, rare earths. But if you look at it, there's a whole lot of other things that China is intimately involved with in both the downstream and the upstream supply chain. So if China decides it's not going to process or is going to impose tariff restrictions on the import to export of various metals and materials, that will change the prices internationally, which may mean that projects which were not viable now become viable, or projects which were viable because China decides to flood the market are no longer economically viable. So again, projects will go nice, that data effectively becomes historical data. Now, I've mentioned a few times this concept of economics, and if you read the SAMREP reporting code of the CRISCO guidelines, you'll come across this term referred to as the reasonable prospects for eventual economic extraction. Now, it's very wordy, and it does come from the SAMREP code, but what you as a competent person need to do is review the data that you've got, and you need to justify why the project you're looking at has the potential to become economically viable. Now, there is discussion in the footnotes and the guidelines of the SAMREP code in terms of, well, what does eventual mean? And again, the discussions in terms of, well, what does economics mean? That the competent person needs to discuss, because we're now looking at the concepts of transparency and materiality when we're looking at things. And when you're trying to declare a mineral resource or later on a mineralized reserve. Which takes us, though, to some of the more interesting things in history. These, again, have been touched on by various speakers, so I'm not going to belabor the point. The Poseidon nickel bubble, which goes back to the 1960s. During that time, America was fighting the war in Vietnam. What had happened is, at the same time, America was sourcing the vast majority of its nickel, which is needed to harden steel for military vehicles, coating of guns. INCO then went on strike, demanding higher wages. Because of that, the nickel price goes up. And there's a lot of exploration occurring, specifically in Australia, in a place near called Mount Windara, near a place called Leverton in Western Australia. There was no regulations at the time, so people could discuss and talk in insider trade and, you know, get the information from the drill at the bar, which in this case did happen. The major kicker of the entire thing was effectively what we would refer to nowadays as a press release, but information going to the market saying that there was a 9.38% weight intersection of nickel on the deposit. That went to the London market. Obviously, everybody's thinking, wow, this is really great. What it turned out, it was actually 0.38. So again, because of someone's bad handwriting and not being able to understand the data, effectively, it led to the spike. The price, obviously, as you can see, collapsed. A lot of people had bought into it with pension funds. There was a investigation inquiry known as the King Commission, which set up things like ASIC and all the new regulations, leading to the JORC code, or the very first version of the JORC code being published. However, we roll on to BRIEX later on. Again, this has been discussed at length. The whole point being that this was actually fraud. One of the links I've just uploaded is the Strathcona report, where the independent audit discovered the fraud was occurring. Effectively, again, what happens, share price goes up, people pile into the market, lots of people invest their savings and pension funds. The fraud comes out, share price collapses, billions of dollars are wiped out to the Canadian market, and it sends shockwaves around the world, which then leads again to another commission. And the Canadian Securities Exchange publishes this document called Setting New Standards. Now, there has been lots of discussion over the last 2 days in terms of, well, insertion rates, where they come from, definitions of certified reference materials or standard reference materials. This is effectively the grandfather document where the first discussions of the 1 in 20 insertion comes in. Yes, as Nicole and other people have discussed, there's Albazov and the various other documents which you can find and download. But this is probably the first document I've come across where 1 in 20 insertion rates, defining CRMs, defining SRMs is actually stated. It is a bit of a thud document to read, but is a nice, interesting historical document. This then later, so BRIACS led to what's referred to as the Denver Accords. The Denver Accords then later evolved into what we call the CRISCO committees, or as you can see here, the Committee for Mineral Reserves, etc., etc. I am the PERC representative, so I'm the European representative on this. And as you can see, there's a number of countries which now sign up to report the exploration results, mineral resources, and mineral reserves in terms of standard definitions and guidelines. Individual codes do vary in terms of local conditions, and the requirements for the person that takes responsibilities for signing off on these documents, which are put into the public domain, also change. So you need to understand, if you're going to be signing off in terms of another code, one, can you actually do it? And second of all, what are the qualifications? So just some of the more interesting ones out there, just for information's sake. In Brazil, for example, it's referred to as a QP, qualified person, and you need a minimum of 10 years of relevant experience before you can sign off in terms of the CBBRC code. If you are going to sign off in terms of the Indonesian code, effectively you need to be able to speak Indonesian, and you write an annual exam which you have to pass. If you do not pass the exam, you're not allowed to sign off, and you're no longer considered as being a competent person. The same holds for India. Again, exams are written to show that you're a competent person, and if you don't pass it, you're not allowed to rewrite until the following exam cycle comes up. In Canada, again, it's legislation, so CIM NI 43-101 is written into law. So if there's any changes, it becomes a lot harder to change because it has to go to Parliament, and there's a whole lengthy discussion. The Canadian code is currently under discussion and review, and is going to go through and is going to change. In general, the changes that we see and I see coming through in terms of the reporting codes and standards is a lot more transparency in terms of project risk and a lot more focus on environmental, social, and governance aspects. So these are just some of the standards and how they get updated. This is already out of date. The Turkish and the Brazilian codes were updated. I was part of the review committees for both of them. So there's new versions for Turkey and Brazil, which are available for download. They are, as I said, all bringing in all the ESG aspects. So PERC, for example, the reporting standard is not actually recognized by any of the stock exchanges in Europe, but it does have an entire section on ESG written into the code. So it's slightly different from the SAM codes, where it's a standalone code. A PERC is actually defined within the code in terms of what we require in terms of ESG. A similar thing with JORC. JORC will be having a lot more focus on ESG, but my understanding is JORC has been delayed because there's been a change in the reviewer from the ASX. But it gets us back to this point. What do we consider as being historical? Well, historical effectively is either by another company or predating the code, which in the case of SAMREC would be March 2000. You also need to take into account, for example, do you have a time limit? So if you're doing a diamond valuation, you've got a 6-month window, so any new data needs to be incorporated into that. We also take cognizance of the other reporting guidelines and standards. So the Canadians publish what they refer to as best practice guidelines. We are trying to move away from the concept of best practice, or rather the word best, because practice evolves over time, and what was best practice, again, has been discussed by several of the previous presenters, changes as we refine the techniques and technology. So what you had back in the 80s, you don't have now. So the ability to store large databases wasn't available then, or it was, but it costs you a lot more money than what it does today. Again, so we're looking at historical operators of the operation, so something that you as the competent person have not been intimately involved with, but you are still required to independently validate that information. Okay. As we move through technology and time, as I said, practices change, we refine things, we have new analytical techniques, we have new computer softwares, we have applications such as AI, machine learning, big data. So all of these, well, again, as Alan Goldsmith described yesterday, not necessarily panaceas to what we're looking at. If the data that's supporting any of our rigorous interrogation processes is not sound, the information, the results we're going to get out are going to be flawed. And again, you can spend a lot of time and money chasing ghost targets or something which is not actually economically viable, but because there's been a mistake in the database, that problem follows through and you end up making really bad economic judgment calls. One of the more critical things that we've seen, or probably more extreme things, is in the case of Kimberlites, where the entire Kimberlite descriptive terminology was changed. If you go down to the bottom, these slides will be made available. You can go and click on the link and you can go and see how Kimberlite reporting terminology has changed over time as our understanding of Kimberlites has increased. Okay, so again, data pre-2013 versus the interpretations now are going to be very different. So again, if you're looking at an old database, you need to understand that, and that database would need to be updated. So we can see it can be of great value, but again, we need to understand the context of how that data was gathered, the people or the company that gathered that data, what reputational issues do they have, and the type of things that you as the competent person would need to go back and research and validate. And I'm going to be taking you through a few examples. It's not going to be exhaustive, it's just to try and frame the data quality and the prior discussions in terms of, well, these are some real case studies, these are the type of questions that you as the competent person should be asking. Okay, so again, with the codes, it's always worthwhile to read the guidance below the definitions. I know a lot of the time, and I'm guilty of this as well, that you read the definition and you sort of skip over the stuff below because you think you understand. It's always worthwhile reading those definitions because, for example, if you look at the last paragraph, the lead competent person has to accept full responsibility for the report. And the implication of that is that the competent person signing off has to assure themselves that the data that the entire report is based on is not materially flawed, and they're prepared to put their name and their reputation on that report. These reports hang around for a long time. Just when you think you've lost, the report has been buried, it will pop up somewhere. No, and I wouldn't say come in the most embarrassing time, but reports don't vanish in these electronic days. As soon as it's on the internet, it will be there somewhere. We can also look at some of the other regulators. So the Canadian Security Exchange, and again, you can go and read the entire report if you click on the HTML link. Went and reviewed the validation procedures that the qualified, so the Canadian equivalent of a competent person did. And they noted that, especially projects in Canada, with juniors, you have a churn. So there's a lot of historical data that keeps on coming through. I've recently just authored 2 NI 43-101s for an exploration projects in Bulgaria, and that data goes all the way back to the Soviet era times. So again, understanding how data was gathered during the Soviet period, what was in the procedures and protocols required of by the state at that stage. It's referred to as the Red Bible, effectively. It's what most Russians and people in Soviet era would refer to. So it's very rigid standards in terms of what you can and cannot do. Okay, but again, you still need to go back and validate and document that data. What have you done? They also reviewed a series of NI 43-101s, and they found that the weakest thing was a description of, well, what did the qualified person do in terms of validating the data that they're basing the mineral resource estimates on. Okay, so again, it's something that, at least in the Canadian market, it is reviewed by the regulator. Again, the 2 reports that I did, that was one of the areas that the regulator came back. I can't take full credit for it because my colleagues in Canada helping me, because they discuss with the regulator all the time, and the regulator was quite happy that the amount of detail that had been put into the NI 43-101s would satisfy them, that there's been a full disclosure in terms of the validation procedures that were undertaken for the data that we used. And we can also look at our data validation in two different ways. We have data validation, as you can see here. So we're going back to the source data. So again, this would be something like you go back to the original core, you take the historical logging, and you go and validate the logging against the core that you can see. We also have the validation exercise. Again, this is something that why you have Sable, because it's now in consistent definitions, there's consistent ranges, and there's consistent data types. Now, just as an aside, one of the things which you should check when you're looking at Excel spreadsheets is the ranges, so upper and lower values. So for example, in something like Sable, you cannot put in a negative density. I have seen during the course of my career doing audits, similar to what Matt has done, that you would often find negative density values in the database or rock densities which are less dense than water. But again, because there's no validation checks within an Excel spreadsheet, these numbers go in, runs through the system, and then when you're doing reconciliation, you wonder why your tonnage is just not reconciling or why your gold or metal grades look really funny. And when you go and interrogate, you discover there's some really bizarre stuff buried in what you're referring to or what the client is referring to as their database. So again, just a nice slide to show how data quality breaks down into the different concepts of data quality. So, you know, the context of the data, the representativity of the data, can you access the data? Again, things that have been discussed more than once and under very specific topics by previous presenters. So probably getting a bit more into the type of things, well, what should you be looking at? Something as simple as the coordinate system or the units of measure. But let's get on to the more specific examples. So coordinate systems, something most of us don't think of all the time. It can be quite important. So this needs an example from an all oil drilling website where the gentleman that wrote the article was demonstrating that if you are not using the correct coordinate system, you could have your drill hole sited in various places which would not make sense and would not be accurate. So you need to understand what coordinate system is that you're working in. So for those of you working in exploration in Southern Africa, it's always worthwhile to be aware that prior to the 1st of January 1999, as you can see, the reference system in South Africa was the Cape Datum. Post 1999, it's moved on to the WGS84 system. Okay, so again, understanding what they mean and not just taking old maps and digitizing and assuming that that is where your data is going to be located in space because the reference system has changed. Other things you need to ask, if you're operating in other countries, do they have a national convention? For example, if you're working in Uganda, Uganda does claim that they use WGS84, but they have a local conversion system. There was a company which I'm aware of, which did exploration in an African country. They didn't take this type of detail into account and then discovered that all the high-grade intersections on the exploration project were actually located 300 meters to the east on the competitor's property. And they spent a lot of time, money, drilling and exploring, but all in the wrong place, and they had to walk away from that. Were local grids used? It's a standard thing in mining operations, even between companies. When I started my career with a company which no longer exists called JCI, adjacent mines had different local coordinate systems. Something as simple as what is your Z datum? Is it mean sea level, shaft collar, or something different? And how was that survey undertaken? Again, over time, the methodology for doing survey has changed and has got more accurate and more precise. Measurement systems have also changed. So in South Africa, on the 5th of July 1974, South Africa moved from imperial measurements onto the metric system. So again, any data prior to 1974, and in fact, there's in some mines there's an overlap as much as into 1975, where inches and penny weights were still used in the database. So you need to understand that data. Was that data converted? A mine I worked on, which was old, had data going back to the 60s. That data was captured, never converted. And we had massive, large areas which we considered as being lower grade reef. We never went back to look at it until one day during an audit, someone said, but just wait, these are in inch penny weights, when we converted it, we suddenly discovered there was a lot more ground we had to mine, which we never thought about. Okay, making sure that you've understood what tons were used. So as you can see, American or British tons. Some American companies which operated in Africa during the 50s, 60s, and 70s would have been operating using the American system, not the British system. So again, understanding where that data is coming from. I'm not going to belabor boreholes. I think we've discussed that more than enough. But something as simple as, well, what core size was used? Again, over time, as budgets have changed and costs went down, core size in general has increased. So earlier core may have been drilled as AXT or BQ, and we're now, in many cases, drilling as maybe an N size or an A or a Q or H size core. So again, understanding something as simple as that. Are you going to redigitize the data? How are you going to capture the data? Something as simple as, is the data legible? Downhole geophysics, how often was the tool calibrated? What type of tool was used? What was the accuracy? What was the precision? Who did the work? Unfortunately, you find a lot of that data wasn't recorded because, again, in the day, those type of things were not considered as being critical. When you're looking at downhole surveys, how was the downhole survey conducted and undertaken? So if you're going back, was it a borehole camera? Was it a gyroscope? What age was the gyroscope? What precision and accuracy were you going to be getting from those readings? Something as simple as not taking that, using magnetic declination, but not taking into account that the magnetic declination changes with time. Classic case in the mine, which I audited, they had demarcated an area which was considered high risk because they had a surface drill hole going through, the drill through dolomites. There was concerns that there would be a lot of water in the hole. You're looking at 3 kilometers underground, high water pressure could lead to an accident. Demarcated the area. 2 days later, the mine captain comes into the geology office and said, oh, by the way, that hole that you said's on the left-hand side of the raise, you've actually picked it up on the right-hand side of the raise, and it was dry. Investigation hadn't taken magnetic declination into account. Looking for collars. Now, these are photographs from site visits I've done. You don't know where those collars are. There's no information on those collars. And it's considered as industry accepted practice in Canada, for example, for the competent person, the QP in that case, when they're doing the site visit, to manually go with a handheld GPS and measure at least 10% or more collar positions to independently verify the location of the collars. There's a whole lot of situations that you potentially run into with locals and collar positions. So if it's farming area, chances are local people will rip out any collars that they can find because you're now interfering with plowing and growing of crops. Other places, if you've used steel casing, if it's a poor area, that's potential money. So again, don't be surprised if you come back and you discover that your nice fancy steel collar has been ripped out to the ground and sold in the scrapyard. Other things, depending on the country that you're in, there's very different views on how cores should be stored. Some of it is due to logistics. Some of it is just due to the fact that, and the mentality still exists, unfortunately, that once the hole is drilled, logged, and assayed, we walk away, we're never going to look at that core again. It's now in the database. And I know everybody's discussed this, but it is still a sad reality which occurs. In this bottom left-hand side, there's over 15 kilometers of core lying there. It's been abandoned in the desert. And the previous owners had the impression they'd logged, assayed, and that was it. Walked away. Those databases have been lost and got corrupted. They were done in Excel. And now the new owners got to go back and try and recapture the data from these holes. In a similar way, as been discussed, going back and potentially resampling pulps and rejects. Again, these are two extremes. So here we have all the pulp samples just dumped, and you can see over time the whole thing has collapsed. Contamination, how many of those are still valid, or how many of those could you potentially go back and reassay without questions being raised about contamination and sample security, is is a big issue. The one you can see on your right-hand side was a well-equipped storage facility, and those, as the competent person for that project, I'd be more than happy to, again, went back and reassayed some of those pulps to validate the assays that the client had in the database. We've discussed QA/QC at length, but again, when you're going back, what are you going to be looking at? What are you going to reassay? The paper by Praseka et al. Is worthwhile reading. I'll post that link as well. Really good article describing in more detail what I've been discussing. Getting into this, and I'm not going to be berated, so if I can finish up quickly, we can have some other people like Keith to discuss this in detail. But over time, assay techniques change.
Around 5 minutes, Mark.
Okay. I thought I had 10, but anyway. So assay technologies have changed. So what can we say about that? Using data in the database, you need to understand the validity of that data, representativity, accuracy. How is density measured? It sounds really simple, but again, this is one of the things more than once people just don't understand the implications of using immersion technique or using pyknometers and what different pyknometers do. So you'll have a density measurement in your database and you have no idea how that density measurement was derived. And going through, this is the final slide before I finish. The whole discussion in terms of, well, is twinning valid? This is a actual example from a large gold project in Russia. So on the left-hand side, that was the interpretation of gold grades based on historical drilling done using Soviet standard techniques. And you can see it was a pretty disseminated, relatively low-grade deposit. Redrilling that deposit using effectively Western standard, or in this case, JORC standard procedures and processes, and applying QA, QC, and all the things that we've been discussing, led to quite a radical reinterpretation of the deposit, and a deposit which was historically considered as being bulk, low grade, and not of too much interest, has now been changed into a much lower tonnage but significantly higher grade deposit, and at least prior to the Ukrainian war, was attracting a lot of interest from overseas investors. And I was hoping to have a discussion, but if you've got a couple of minutes, this is the time for discussion. And I'm sure people like Keith and Matt and everybody else which has contributed can give some examples of things that they've experienced. Thank you.
Thank you, Mark. Any questions, comments, discussion points? Marcia, is there a hand or a wave?
It was a clap. Sorry.
Sorry, I'm getting used to Zoom myself. Thanks so much, Mark. Any questions for Mark? Sorry about that in the background.
Mark, sorry, I didn't have my hand up, but excellent talk. Thanks very much, and a timely reminder of the governance side, especially of where good data and good sampling and good governance thereof fits into our overall confidence in our resources. Just going back to one of the comments that you made, perhaps slightly off the point, but the ESG, and maybe you can comment on how that's sort of coming into our thinking into or major way that we look at our resources currently, and also how we measure that and how we do the governance on ESG issues.
Can of worms, Matt, you know that.
Yes. Sorry.
Okay. It is ESG, as we're all aware of, with going green and net zero, it is becoming more and more important. A lot of the stuff we as the mining industry have done, because we all, I think most geologists tend to like nature, and we're not just going to rip a hole in the ground if we can possibly avoid ripping nasty holes in the ground. The problem comes in, there's still enough people out there in the industry which have been quite naughty, and there's been issues like Juukan Gorge, tailing dams failures in Brazil. So again, there's always a need for regulation. So what is becoming more apparent, and I'm going to refer to the PERC code because I'm a little bit more familiar with PERC at this stage, is when the competent person is making a commentary about especially the RPEE aspects. The competent person must now make a comment along the lines of they have reviewed the environmental data from the competent person's point of view. They see they're not aware of any environmental liabilities. So you're not going to be doing your exploration in the Kruger National Park, or you're not going to be building your open cut coal mine next to the Vaal River. So those things need to be flagged. Social, have all interested and affected parties being consulted, and it's no longer just a tick box exercise. There needs to be documentation coming back from those interested and affected parties, but specifically local community groups. And again, have all people in the local community have the discussions involved all people, and the representatives are they actually representatives? So those of you, if you cast your mind back, was it 3 or 4 years ago, there was a whole discussion down in Transkei about the heavy mineral sands operation, and the representatives turned out they weren't the representatives, they were pressure group, and all those issues. So everybody has to be involved now. Governance has always been the sticky issue. Now, the latest discussions, at least at the CRISCO level, is that, and this is unofficial, the latest discussions where CRISCO is not going to try and define governance, because and if there is any governance, it's got to be the governance at the project level. Are the company's procedures and standards being done? Because it becomes very difficult to start defining things which change from country to country, or start getting you involved in stuff which is way beyond the scope of reporting a resource and reserve. For a competent person to give comment on the board composition and remuneration policies of a company, the competent person is just, or the QP is just not in a position to do that. So Matt, hopefully I've tried to answer the question. Or not? Stunned silence from Matt.
No, I was on mute. Thanks very much. That was excellent. So it's just worthwhile us all keeping it in mind, because it is something that everyone's trying to get their minds around going forward. Thanks.
Yeah. Sorry, just one other thing. Sorry, Tech, I'm not trying to cut into anyone's time.
No worries.
So for everybody to be aware, I know I'm operating like Matt out of the European context. Now, the EU have recently tabled what's referred to as the European Critical Raw Materials Act. One of the things in the European Critical Raw Materials Act is reference to the UNFC, so the United Nations Framework Reporting Code. So what that implies is any strategic projects in Europe which are going to apply for EU funding must, above and beyond you reporting the project in terms of a CRISCO code, if you want to get EU funding, you would need to then apply the UNFC framework as well to doing the classification. Now, that's only like an additional column or two or paragraph in your report. But again, with the focus on net zero and circular economy and stuff, there is a growing directive at the government level, and where the UN gets involved. So like Africa, where some of these things will probably become something that you as practicing geologists will need to become aware of, especially if you're operating outside the borders of South Africa. Anyway, finish now.
Today I'm going to be talking about who moved my grade. And I realized that a lot of the presentations have been very technical and have gone through a lot of the reporting codes. This great presentation by Mark just before me. And so I'm going to take a little bit of a different angle and for us to just be a bit more introspective, I guess, to some extent, and take you through some of the way I do things on my side. So this topic is quite an interesting one, who moved my grade. It's a series that I've always wanted to do. It's something that way back when, I think 2008, 2009, Ina Dom actually suggested it after Who Moved My Cheese came out. And So I'm finally starting the series that I'd like to put together. This is just the introduction, so it doesn't go into any major depth or anything like that at this point. But given that that's already been covered, I think, by the great speakers that you've had yesterday and today, I think I'm okay. So let's just see if this will move on. Ah, yes, okay. So those are my topics for today. So if I had to Google high-risk jobs, it's quite fascinating what comes up. I think some are quite obvious. An airline pilot, the military, a security guard, a police officer. Unexpectedly, a registered nurse came up. And I started to think to myself, well, you know, if a registered nurse who could be exposed to diseases and various other things, it comes up as a high-risk job. And the roles that I've had to play over the years, you know, the jobs I've had, the roles I've had to play, making decisions based on limited information or only a few drill holes, having to decide where do we need to drill more? Do we walk away based on 4 drill holes? What would the investment criteria look like for a project with only a couple of drill holes? Do we continue to a concept phase or PFS? And really, we just know that the cost of investment into mining is really high risk, but high reward. It made me wonder, should I be on that list as a high risk job? And, you know, I think all geologists should be on the high risk job, you know. Here I was looking at a colluvial iron ore deposit, and it was largely supported by historical pit information. There were thousands of jobs at stake, and I had to make the decision as to, is there a resource here? What classification does it go into? And more importantly, what category to assign to that project, just based on these historical pits? Would it one day become a large open pit mine, which I'm sure you all recognize on the right-hand side? And so, yes, I think that our job is actually high risk. So bearing that in mind, and with the understanding that data is what supports our job at the end of the day, I think we need to really be considerate as to how we handle data, what data we accept, and more importantly, how we use that data for whatever form that may be. In my world, it would be for classifying into a resource category. So let's take a step back. When I think of data, I think of it as a box of apples. So I go to the farmer's market and I buy myself a massive box of apples. And when I open it up, I see one really bad, rotten apple. And I start to think to myself, does that one apple in the box concern me? Does it make all the other apples look bad? Where did these apples originate from? Do I need to wash them first? And similarly, when we look at data, we actually need to take a deeper look, not just take it as face value. And I know a lot of people have spoken to that today, but you know, you sit there and you say, well, does that one data point or that data set that you know may be a problem, does that have an influence on the whole data set? And I think to some extent, it does cast some doubt on the remaining data. But what is more important is to isolate that data and to understand how it would affect your workings, what is it going to be used for, and more importantly, to document it. So we've heard about databases and flagging information in databases, but understanding your data is extremely, extremely important. And just like with apples, data needs to be stored under the right conditions. And this brings me to the concept and the approach that I use when I'm looking at a new project or a new data set that comes to me, and I call it the chain of custody. So I think we all know what a chain of custody is. Well, I hope so anyway. It indicates the collection, the sequence of control, the transfer, and the analysis of data. And really, what does that culminate into? Evidence. And maybe I've been burnt one too many times before, but certainly making sure you have evidence of the work that you've undertaken, the analysis that you've done is becoming increasingly more important. And particularly in the world that I'm in right now, which is more transaction-based, people don't want to just know that you've checked it. They want to understand how. So in order to do that, we need to understand the flow of information. We've heard already under sampling theory and other that area is additive. So understanding how your information flows and how your data flows through the chain of command is really important, because as you pick up more error through that flow, it actually adds to the uncertainty you have at the end of the day and the fun task of deciding on a classification category. As I mentioned, now, as you move through that value chain, you're going to be picking up more data. So it's not just our exploration data that we focus on, but trying to understand how bulk samples, grade control, bulk samples, reconciliation, and the list really goes on. Your analysis as you review each data step also becomes data inputs into that full chain. And so keeping working documents and working papers is incredibly important. So I'm not sure how familiar you all are with the auditing world, but we use the word working papers. They are crucial for the way we work, and they don't necessarily reach our clients or an audit committee or what have you, but certainly they can be pulled at any stage, and they document everything in detail. But I'm not saying this should form part of the full technical reports, but rather to be kept as evidence. And the most important part of a chain of custody and evidence keeping is really to make a decision at the end of the day. And I think that we've become very familiar with checklists and have we got this, have we done that? But it's the interpretation and opining at the end of the day to say, actually, yes, as a competent person, I'm comfortable with that information to go into my report and to accept it and not to downgrade perhaps a classification or a category. So how do I work? This is my chain of custody. This is the approach that I like to take. I like to map out as much as I can with the three main criteria, the three main principles of the reporting codes that we know, and to look at each step with a view of competence, materiality, and transparency across those exchange of data throughout that resource reporting process. And really it's to look for uncertainty and maybe some I guess generally we're dealing with uncertainties and uncertainties. Oh my gosh, I can't speak. I'll just skip that one. And this causes many problems globally. I think more recently, we've had some topics on classification around resources, when to actually classify as a measured category. And there's been some debates within the circle that I'm sitting within. Sometimes people request for more drilling. Yet there's still that level of uncertainty in that data. When you think about it, you're taking a tiny little sample, which then gets split again, and its size is reduced, and you're basing a decision on that tiny, on that one tiny sample, where there is a fear of bulk sampling or trial mining, which if there's still some representativity adhered to, can be quite useful in informing a classification. But I think these are the topics that I really want to encourage people to have those open debates, and not just to blindly say it's not in the code or it's not in my checklist or it ticks these boxes, but to actively say, well, for this project and this case and this opportunity, perhaps we don't need to do more drilling. We could move to, say, for example, a bulk sample. Obviously, you'd still need to understand density and so forth. But yes, this is the approach I like to take. It's the data flow from the data sources, which could be historical, current data, bulk samples, grade control samples, what have you, and then moving through the flow. And then the working documents that I like to put together, I'll show you in the next slide. So if I pick Collar survey as an example, and I think, Mark, I was listening into your section and you ask some of the same questions. You would typically ask yourself a few questions around those collars. If, for example, you want to sign off on the surveying, you could also visually have a look at the data, but it comes down to that conclusion at the end of the day. So in this example, we had BH002, where clearly it's sitting above the topo. But on further investigation and understanding of this project, we realized that that was a historical drill hole and we wouldn't exclude it in our resource estimation and classification, simply because it still indicated what they were mining previously. And that yellow orangey line there represents the pit that now exists there. So, you know, again, it's not just going through your checklist and saying, okay, so many drill holes are outside of the topography. It's asking the question, why? Is there a reason for it? Can it be documented? And then coming to a conclusion, is this acceptable because of X, Y, and Z? Others may use checklists. I love using checklists. I think they're great ways to quickly come to some understanding of what you're looking at. But again, I caution not to use them blindly. You can tick everything looks green, and you move on and you classify. But to actually analyze, understand, and interpret seems to be a rare skill these days. What I like to do is actually provide a status on each of those questions that I've asked, and then to provide a risk rating as well, which I think is on the next slide. Yeah, and I actually roll that up into a likelihood, a consequence, and an overall risk rating. And I find this is useful because you can often find where your key problems may exist within that process. One other thing that I'm finding is that the investors that come to see us are becoming increasingly tired of these long reports that we write. So certainly some of the stock exchange reports that I've done recently can be long 1,000-page documents. But when you come to the investors, they really want something quick, neat, tidy, easy to read, easy to understand, but still has the salient points that cover the requirements of the reporting codes. And this is also why I quite like this way of looking at my data. Once I've gone through the in-depth review and my working papers, to pull it into something like this, which then can actually roll up into some of the short form reports that I'm sure you've seen in the public domain. A lot of these were done in the old days by Venman, Deloitte, and so forth. But we are starting to, I would love to show you some examples from EY, but unfortunately, most of them are confidential. But our clients are liking these. It's quick for them to get an answer, but you've still got those working documents in the background to support what the work that you've done. Okay, so why did I use the topic Who Moved My Grade? I'm sure you have seen the book Who Moved My Cheese. It's something I really, really enjoy. And people use it for all different reasons in their lives. It might be they're changing jobs, or perhaps, you know, it's helping with some of their relationships or interactions with people. Maybe they got big decisions they need to make or what have you. If you haven't read it, do read it. I quite enjoyed it. It's a quick 1 to 2 hour read. But certainly, I think that there are some principles that we can take even for mining. So what are some of those learnings? You'll see them on the left-hand side. Smell the cheese often, so you know when it is getting old. Well, simply put, if you don't have a handle on your data, if you don't have a handle on the veracity of that data, verification and validation of that data, you can't really do much with it, or you may be using it erroneously. Keep an eye on your data. Don't, the next one is anticipate change. Get ready for the cheese to move. So we may move into a new area, or we've mined out one part of an operation or a project, and we now just flag that data in the database and we say, okay, we're moving on. We don't need that. Thank you very much. Thank you for all that drilling, but it still holds valuable information, particularly around reconciliations and other. And so, you know, I really do like the concepts of Who Moved My Cheese. And in terms of data, is just to always keep looking at your data. You may even find new avenues. It might lead you to another deposit, but constantly reevaluate it. The other benefit that I guess I've had over the years is that the data that I've accumulated helps me to understand or provide direction or decisions for other operations that I might be looking at the time. One of the other concepts I really like in the book is that of the maze. And you have these 4 characters who move through the maze until they find their cheese. And it is only 2 of them that decide to leave when things don't look good. And in leaving and taking a new path, you actually could find, you know, search for new cheese, right? And so I guess the message there is always look at your data and see if there's another way that you could use that data or interpret it to perhaps find another deposit or to indicate where you may be going in another area. And I think oil and gas do that really, really well. You know, they have the concept of basin to super basin. So you don't necessarily need to go in and spud new wells, but rather to say, I've done some seismics, this indicates a basin similar to another, and the potential for oil or gas or what have you is quite high. And based on that and probabilities, they may go in and spud some wells. So there's definitely learnings there. There's also never any dead ends, in my opinion. So once you've walked a path, you realize that it wasn't the right path to walk. And that gives you useful information on what not to do, or perhaps a metallurgical or processing methodology isn't going to work. And it also doesn't mean you close it off forever. There may be cheese at a later stage. Is there a question? Oh, okay. Good. And don't be scared. Just make a start and take a path. Oh, gosh. Okay. So mine is quite a short presentation. This is my last slide. So Mark, you could have gone on as you wished. But, you know, I guess there are a few different types of geologists. The list is actually endless, but you get academic geologists, commercial geologists, economic geologists, volcanologists, exploration resource. There are so many different types. But I actually want to reclassify geologists and ask you all today what type of geologist you'd like to be. Within the book, there are 4 characters. You've got Sniff, who detects change early. You've got Scurry, who takes quick action. And we've got Hem, who resists change. And lastly, we've got Core, who adopts change with time. So what kind of geologist are you going to be? Are you going to be the checklist geologist who ticks off the checklist and gives it a thumbs up? How about the fly-by-night? You do your quick back of the matchbox check and you give the thumbs up based on that, but you haven't done any deep analysis or anything like that. There's this is how we've always done it, geologist. I guess that's self-explanatory. You're just not open to innovation, new ways of thinking, or you can be the critical thinker geologist, and that would be to actually analyze, to reinvent yourself or the information in another way or form to help you to find new paths, to find new projects, and certainly does a lot more deeper analysis. And that's really it. So I did hear about this quite late, and I've only just got back from very long leave, but I hope you enjoyed that, and I hope it gives you some thinking around how you should be looking at your data and what kind of geologist you want to be at the end of the day.
I'll get straight into it. I'd like to say firstly, how much I've really enjoyed this conference. It comes at an excellent time and an excellent reminder of the foundation on which we build our businesses. I've really enjoyed the talks right from the beginning, Kathleen's reminder on the value of looking at density and measuring it properly. The keynote talks, I think, have been excellent, but all the talks, I think, have just been absolutely fantastic. Mark's well-researched talk, reminding us of the governance of the data, etc., and Marsha's on data integrity and databases. I could go on. I've just struck a chord with me, and I've really enjoyed it. I'm going to come back to a number of themes because a lot of what I want to talk about has been mentioned by a number of speakers over the last 2 days. But the issue that I want to talk about is the value of good data. This was sparked, this interest in this topic was sparked by Marsha, who asked me a few months ago, how do you value good data? And I have come back to thinking about it. And I suppose what I'm going to show you is how do we put a value on bad data? So trying to answer the question in the opposite. But I want you to know that this is work in progress. I think it's something that we should continue to think about, and that we should continue to try and get our minds around not only what I'm going to show you in a very broad sense on how we put a value on bad data, but how do we put a value on good data? You know, if I just sort of step back on this conference is a really timely reminder of the importance of that foundation on which we build our industry. Our geological understanding, allied with the data that we collect, goes into our resource models, goes into our mine plans, goes into our financial models, and ultimately goes into the money that we raise to build this industry, which basically makes everyone's lives better, from motor cars to fridges, to all the things that we do, to our cell phones, etc. So I don't think at times we pay enough attention to this foundation, and that's why I think that this conference has come at such a good time to remind us of that data foundation. So I'm going to share my screen to go straight into it, and share screen, there we go. Now I want to just show a bigger picture view of the industry, and this is just to put it into context. How big is our industry? Basically, if you add up all the listed companies on the stock exchange, plus all of the support industries, you probably get sort of between $2 and $3 trillion in terms of the size of the industry, dominated by a small number of large companies. You can see BHP, Rio, Fortescue, Vale, etc. on the right-hand side, and dominated by a number of commodities on the left-hand side, the big ones being gold, iron ore, aluminium, and copper. That's a little bit out of date. It has changed a bit. Ones like graphite and lithium are bigger nowadays. But you can see relative sizes are probably pretty similar. To put it into context, though, oil, which is the big circle on the left, is 3 times the size of the total commodities industry in the world. Also, to put it into context, the minerals industry is about 1/3 the size of the banking industry if you measure it on the same basis. It's still big. $3 trillion is a seriously big industry. It's not the biggest though, but it plays a critical role in the quality of life that we all live. What sets it apart from banking though, we go to the next one, is that it is incredibly capital intensive. You can measure this in different ways, but one of the ways of looking at it is how much we spend in terms of capital in expenditure every year, and it can be in terms of all our greenfields projects, brownfields projects, our sustaining capital. It can be up to 20% of our market capitalization. That does include mergers and acquisitions. Every single project, and there are hundreds, if not thousands of them per year, needs to be valued. But every single one, the critical thing is that it's underpinned, every mining project is underpinned by the sampling data and the geological data of the ore body under consideration. This sets it apart from many, many other industries worldwide and makes it a very special industry. Siobhan, I think, talked about all the various players in the industry. I've played in a number of those different roles and a number of different ways that I've operated in over 42 years. But I can say that it has been an exciting industry to be involved in. It provides a level of challenge and interest that I would not have got in, say, banking. So that sets the scene in terms of the industry. It's big. It's about $3 trillion. It's capital intensive. The third thing I wanted to mention is that we study our projects in terms of a project pipeline. And we've mentioned this a couple of times. Keith brought this up as well. We have concept study, pre-feasibility, we have feasibility studies, execution, and then we run mines. The way that we study these projects means that at each end of a phase, we have usually a toll gate. And that toll gate is a check on the information that we've got up to that point in terms of justifying further study or further execution or raising money to build a mine itself. At each toll gate, we actually need to check the ore body modeling and we need to check the underlying data that goes into that ore body modeling. And that is what Keith mentioned, the audits that we do throughout this project pipeline, whether it is at a project level or at an asset or an operating mine level, is a critical component of our overall health of our industry in terms of ensuring that we get it right, that we build the right mine, and that we operate it at optimum level. We don't always get it right. And I want to start off with going back to what Mark was talking about, Bre-X. It was a seminal moment in the overall history of our industry. It was the biggest mining scam ever. It was in 1997. I'd been in the industry about 15, 16 years at the time. Didn't realize the importance, subsequent importance that Bre-X would play in the overall way that the industry operated. Just to give you a bit of history again, it was in 1995, Bre-X claimed that they discovered a major deposit in Busang in Indonesia. Their share price went up from a couple of pennies to, I think it peaked at 286.50 Canadian dollars. And that gave it a market capitalization of 6 billion. They claimed that they had discovered a mineral resource of 70 million ounces of gold. Put that into context, that would have made it one of the topmost projects or mines in the world if it was true. Generally, in those days, in 1997, we used to think that if we had 1 million ounces, we were doing pretty well. At the time, the company that I was with had just listed on the London Stock Exchange, and we had declared a mineral resource of 3 million ounces, and we thought we were really good. Our share price, Bre-X, happened just after just before the listing that we had, which was Randgold, and our share price collapsed, and we didn't raise as much money as we wanted to. And so Bre-X had a significant impact on the company I was with at the time. However, as Mark pointed out, the Bre-X collapsed in 1997 after the gold samples were found to be fraudulent. It was alluvial gold that had been salted. The boreholes had been salted. And certainly it was the biggest stock scandals in Canadian history, and is still rated as the biggest mining scandal of all time. So this gives us a value, and the value of false data or fraudulent based data I've put as the value of the market capitalization of Bre-X at its peak of 6 billion Canadian, which equates to about 4.4 billion US dollars. There have been many, many mining scams. I want to point to another one in South Africa, which was one that I've been researching over the last couple of years. Let's just finish that story first. The characters involved in Bre-X, two of them are showed in the middle there, John Velderhof and Michael de Guzman. John died a couple of years ago in Manila, and de Guzman fell out of a helicopter. He's the one in the green t-shirt there, shortly after the Bre-X scandal broke. And many people say he was pushed, and some people say that it wasn't him because his body was not positively identified, and I think makes some very interesting stories that still go around today. One of the things that we don't recognize, if you go look at the left there, is how much money people made out of Bre-X before the scandal broke. So the moms and pops who bought the stock at 3 or 5 cents per share and sold out before the scandal would have made a lot of money. And that's often the case in mining scandals, that people do make a lot of money out of it, although those who were holding stock at when the scandal broke would have lost everything. And that's where we get the value of 4.4 billion. So going to a more local example, and this is just to show that mining scandals are not a new thing. This is one that I've been researching, which is the Simonsberg, or the Goede Verwachting mine, those of you who know the Western Cape would recognize the Simonsberg, which towers over Stellenbosch. And there was a silver mine, which was granted a mining license in 1743 to a guy called Franz Dietrich Müller. He claimed to have found silver there, and actually what he had done was melted down some silver coins, mixed it with rubble, convinced the VOC that he had found the silver, and they put in an enormous amount of money, which I haven't converted to today's terms, but it was in the tens of millions of dollars. He got away with this for 6 years before he was found out, and the mine itself didn't produce a single ounce of silver. The cost of that, we can calculate tens of millions of dollars, but there was a huge reputational cost to the VOC in the 1750s when they were trying to develop silver in the Cape at all costs to compete mainly, I think, with the Japanese silver mines at the time. This is interesting because not only was it the first mining license granted in South Africa, but it was the first mining scam. Certainly not the only one. It would be interesting to document all of the mining scams that have happened in Southern Africa and to put a dollar value to each and all of them. Moving on, BRIEX, one of the major outcomes, as Mark pointed out, of BRIEX was tightening up of regulations throughout the world. JORC itself had been started in 1972, had really got going in the 1970s. BRIEX gave all the mining codes throughout the world a great impetus, and JORC itself, I think, has gone through a number of iterations since it was started. SAMREC itself, the Canadian codes, PERC, which Mark's involved in as well. But I just want to turn to one of the clause 19, which is under exploration results. And it's quite clear that any public report, which is just as a reminder, any report that we use to describe an ore body and ore body's potential, and it's in terms of exploration, mineral resources, and ore reserves, must contain all the information that is relevant and necessary for a reader to make a balanced judgment of the significance of that. Critical in this is not only the geological context and method of sampling, but the sample intervals, the locations, the distribution, dimensions, and location of assay data, how we analyzed it, how we aggregated it, on what land it is, and also comply with, in JORC and SAMREC as a Table 1, any of those requirements that are material to an assessment. So what is material? We'll come back to that point. And what is an assessment? An assessment is, purely and simply, if you go back to the purpose of a public report, is would you put money into this project? Your assessment, and usually through analysts and specialist people, as Siobhan was talking about, is how would you invest in this? And have you been given all the material information that you need to make your balanced judgment of whether to put your money into this investment, whether it's into a new investment or a new project or into an existing stock or share. I worked on the Johannesburg Stock Exchange as a mining analyst many years ago, and this was a new concept to me at the time, where I'd been mostly technically focused up until the point that I worked on the exchange. And it changed the view that I looked at technical information quite considerably, and especially in terms of material information. I had previously looked at various aspects of a mining project in very much a narrow technical focus. Working on this exchange gave me that financial view of what actually really makes a mine or project successful in terms of financial performance. This is Table 1, and I won't read this out, but if you look at what they give here in terms of the JORC 2012 standard, I'll just highlight one or two things. Firstly, the quality of the assay data and lab tests, verification of sampling and assaying, and location of data points. And those are the three that I'm going to be looking at. In terms of quality of assay data, the third bullet point there highlights the issue of quality control procedures, and it mentions standards, blanks, duplicates, external laboratory checks, and whether acceptable levels of accuracy, i.e. lack of bias and precision, have been established. I believe, as Keith was pointing out, and a number of the discussions have highlighted, that we highlight the deficiencies in a lot of our QA/QC procedures and results, but we don't always act on them. And I'll show you some examples of that. I'm going to turn to, firstly, the data location. And this is an area that I'm particularly concerned about, because I think insufficient attention is paid to the precise location of sampling data. And I'm not just talking about X, Y, and Z coordinates, where I think the Z coordinate has been one that we've had a significant issue with in the past, which has improved through proper topographical surveys such as LiDAR surveys. But many historical holes, and this has been mentioned today, have not been adequately surveyed, not only for their collar location, but also downhole surveys. So many holes, especially inclined holes, which do not have downhole surveys, we have the samples in the wrong position. And this can have a significant impact, not only on the location of the samples that we're using for the models that we build based on them, but on the ore body models themselves. So multiple coordinate systems has also been mentioned. That continues to be an issue. And if I just look back on the last 12 months of projects that I've worked on, at least 60 to 70% of those projects have had issues with coordinates and coordinate systems. Those have sucked up an enormous amount of time, and you can put a value to time. So you can actually tell how long you've worked in terms of fixing the problems with coordinate systems. And so you can put a value on poor data. This is, I just want to highlight the example of a project that I've worked on and off since 1999. And this is the Pairing lead zinc Mississippi Valley type deposit in the old Western Transvaal. It was a pretty good producer, about 500,000 tons of zinc and about 85,000 tons of lead. It milled 20 million tons of ore, average head grade of 2.6% zinc and 0.6% lead. It closed in 2006, and it's been through various studies on reopening the deposit. It is currently still closed. The point I want to mention, though, is that when the original exploration geologists laid out the grid for the exploration, they laid out a local grid, which was 0 to 1,500 meters in the x-axis, 0 to 1,500 meters in the y-axis, and 0 to 1,500 meters in the z-axis. So you could have the situation of a point in the middle of the deposit which had exactly the same numbers, and you wouldn't know if it was X, Y, or Z. To compound this error, the surveyors recorded all grade control drilling as YX, not as XY, and were transposed in the database. And it took my colleague Colin Carey about 3 to 6 months to unscramble this database. And even then, I'd say about 30% of the data was discarded as not being able to be unscrambled. No transformation also was done to any regional or national coordinate system. And to this day, because the original grid was rotated, to this day, even now the coordinate system, although we've done the best that we can, is still subject to a certain amount of error. One of the checks that I encourage everyone to do is to take the coordinates database and to plot it in Google Earth. So what I found is that in a number of cases, I won't say many, the stated coordinate system is not the coordinate system that is actually used. And I refer here to particularly local coordinate systems such as Sergas 2000 in Brazil, local coordinate systems which have a minor offset to UTM, the universal transform, such as at Sadiola in Mali. This is a particular one which I'm showing here, which is a diamond mine in Angola, where I found that the coordinate system had an offset to XYZ of about 30 meters on the x-axis, about 60 meters on the y, and about 30 meters on the z. And once I plotted it in Google Earth, it didn't plot on the coincident with the mine itself. And what you see in there is the corrected Google Earth and color coordinates. It is worthwhile doing this check because it happens more often than you think. The issue here is that there are a myriad number of coordinate systems throughout the world. I'm showing you on the right-hand side, just opening up a couple of them. They are regional, they're local, they're global. Often we don't get them right. We state one coordinate system when we're using another, and often that is because it goes back historically. I think Mark mentioned the old Cape system, which then was LO, and then we now use UTM. LO is a particularly difficult system to use because it is in the third quadrant of the coordinate system, so it increases to the left and increases down, and it's very difficult to deal with it in Cartesian coordinates. And those of us who are well versed in the Witwatersrand would know the problems of dealing with LO coordinate systems. So that is something that we need to be aware of. Getting our samples correct in space is one of the key issues. If we get it wrong, I try to go through a lot of my notes on previous projects that I've worked on where it has been incorrect, and it can vary from a fairly minor cost to fix it to much higher cost of getting the mine plan or the infrastructure placing wrong. I've seen infrastructure placing that has gone onto ore bodies because of incorrect coordinate systems, and has actually had to be moved. So I've made an estimate of the cost of getting our coordinate system wrong, coordinating location cost, and it's anything from $1 million, it might be a bit lower than that, anything up to $1 billion cost of getting that wrong. So that's the location cost, and that's my estimate of that. I think we need a bit of a database to be able to narrow down this range and to actually put a couple of more examples onto it. But certainly from my own experience, I can start doing that, but I'm sure everyone's got their experiences of location cost and it's lost value to the company. Into a critical issue, which is our sampling data. And the question was raised, how much QA/QC sampling should we do? The rule of thumb that I've come across in most of our audits is anything from 10 to 20% of our submitted samples to any laboratory of question, including what the laboratory submits as its independent checks, should constitute about, let's say, about 15% of the total number of samples. The value of these is that we get confidence in our overall database that we're working on, but in particular, as has been pointed out, do we really act on this? So I want to go through the kinds of data that we get. These have been mentioned. Firstly, blanks. And I've given you a report that I wrote recently that is just going to be used, and I want to use this particular report to illustrate the value of getting our information or not having good information. So in terms of blanks, we had contamination. Although there was no indication of consistent bias, the level of contamination was material. And in terms of the resource, the mineral resource estimate, although the contamination reduced after 2014, and the remaining contamination appeared to be misallocation, there was a fair amount of noise in the samples. The CRMs were maybe mislabeled CRMs, but there was also a period of over or underestimation bias, but no consistent bias. Umpire samples, which are the ones submitted by the laboratories between to check on their own assays, were reasonably good, but there was no bias observed as well. There was no bias observed in the duplicate samples, and although there was variation in the coarse rejects, there was no bias observed there. Other types of samples that we might submit would also come into play, but these would be the most important ones: your blanks, your certified reference materials, and your field duplicates. In terms of blanks and CRMs, the comment has been made is that we actually don't make much of an attempt to disguise them sometimes in terms of submission to the laboratory, where they can pick up exactly where whether it is a blank or a CRM. And they often give it special attention when they notice it. They need to be disguised, both in terms of numbering and in terms of rock or the type of sample that's submitted. Going back to this particular example that I've given you here, the impact of this was if we go back down to just as a reminder of the resource classification with the vertical axis on confidence in the resource, we have to take the various amount of information, the various parameters into account when we classify the confidence in the resource. QA/QC is a critical part of determining that confidence. So whilst in this particular example, we would be tempted to declare our resource as measured, the QA/QC is a large component of downgrading that resource to indicated. Siobhan also mentioned the current trend, and I want to mention it as well, towards not really wanting to declare measured resource until you have a mine and you have reconciliation, according to some people. I don't buy into that. I think you can still have measured resource in a project where all of your parameters are reach the kind of confidence that you as a competent person would be happy to sign off on. In this particular example, it would have been measured resource from the amount of drilling, from the amount of sampling that was done, from the amount of, from the integrity of the resource modeling, but it was downgraded to indicated, and I supported that because of QA/QC issues. Lower confidence resource classification has an impact on our ability to raise capital funds, to develop operations or to keep operations ongoing. And basically it's a failure to raise capital. Bottom line is that we lose investor confidence in not only in our projects that we're presenting to investors for investment, but also in the ability of our own industry to present good projects. So it has impacts not only investor confidence, but it impacts credibility of the profession itself. Turning to the third point that I want to talk about is that database integrity. I've made a sweeping statement at the moment, and that's really because it's something that I've been tackling with over the last couple of years. And I've said that's probably the single biggest issue facing us in terms of confidence in our mineral resources. So many times I've been given databases that just do not stand up to scrutiny. And that's anything from the XYZ coordinates to the QAQC, to the actual numbers, transposition of numbers. I still see uncontrolled Excel spreadsheets as being prevalent. Nothing wrong with it, as long as they're based on an underpinning database, which we can go back to, which has integrity and governance. Well-organized data, proper QAQC, appropriate checks, balances, and in particular sign-offs is essential to a successful mineral resource audit. This has been spoken about. I mentioned it earlier. I am usually absolutely delighted when I go into audit a mineral resource and I find that a database has been captured in a database with integrity, with the appropriate checks, and with sign-offs. Issues like transposition of columns can render a database unusable. I came across this one about 2 years ago, where in a Witwatersrand gold mine, which had closed down and there was trying to raise money to reopen it, the stoping width and the channel width had been transposed. And in fact, to make matters even worse, the channel width had been discarded. So you had a gold grade in centimeter grams per ton, as if you're familiar with the Witwatersrand, and a stoping width, but no channel width. And this had played a major impact, made a part in the investor, American investor, not deciding to put their money into that particular project. So this is a quote from a report that I wrote about 18 months ago, in which I was particularly happy with the database. And I'll draw your attention to the second sentence, in which I say global leading practice, drilling, course head management, database management, and sign-off procedures, modeling approach, and resource classification. The part there that I want to highlight is that the database management and sign-off procedures was a critical part of this particular operation getting a very good audit. These audit reports, I'm not sure if it was mentioned over the last 2 days, usually go to the board, to the Risk and Audit Committee, or whatever the particular name is in that particular company. And so these carry enormous weight. They, in many ways, are a scorecard on the technical team that has developed the mineral resources. And so companies pay particular attention to them. They often are published in the annual report as well. So what you write in these reports has enormous weight. Things like being able to sign off on the database integrity and the database management is particularly important. Not being able to sign off on it, on the other hand, has a major impact on credibility of the technical team, but also on the ability of the company itself to raise money if it's a project finance that they're looking for. The bottom comment there is that a scrambled database can set a project back by years, and you often, a scrambled database, the only way to actually fix it is to re-drill your deposit. And I've seen this before. Imagine the cost of re-drilling it. So we can put a cost to a database integrity. I think I've tried over here. I haven't. In the summary, I'll show you what I feel that would cost us in terms of value. I just want to go through, how am I doing for time? About 5 minutes just of a couple of quick examples of particularly bad database sampling and database issues that I've come across over the years. Certainly not all of them, but these are ones that I want to highlight. Bauxite, I've done a lot of work in Guinea, Suriname, West Australia, and Cuba. Not Cuba, sorry. And a particular issue there is that in your bauxite, you have aluminium silicate, which dissolves in, only certain minerals dissolve in acid. And they dissolve at different temperatures. And so gibbsite dissolves in sodium hydroxide at 143, and that's what's called the available alumina. Reactive silica is a key contaminant as it increases plants. However, in many deposits that I've come across, the total alumina is usually used, and reactive silica is not used, but the SiO2 as a sampling parameter is used. So this gives you an idea of what the landscape looks like in Suriname. And the problem that we come across is that in the early years of development, they only analyzed for Al2O3 and not available alumina. They didn't analyze for reactive silica. And as a result, their recoveries were overestimated and their costs were underestimated. And it's not the only project that I've come across that was rectified fairly early on, but a number of other bauxite projects that I've come across have made this mistake, which most of them has been rectified, I must say. Going on to mineral sands, this is a beautiful photograph of the Richards Bay Minerals, Pond 4, I think it was, or Pond E. In a mineral sands deposit, you get a number of heavy minerals. It's usually dominated by ilmenite, or some are dominated by zircon, especially in East Africa and some other areas. But you get an assemblage of minerals, some of which are valuable and some of which aren't. Only a certain proportion of the mineral assemblage can generate revenue, typically about 70% of it, although it varies from deposit to deposit. What often happens, as I've discovered, is that your total heavy minerals and your valuable heavy minerals get mixed up. And often people refer to valuable heavy minerals or total as valuable, and it's not the case, only a certain proportion. And this is an issue that I found as well in platinum. Nicole, you would have, I'm sure, come across it in your experience, where your assemblies of platinum group metals of 3 plus gold is often mixed up with the assemblage of 6 elements plus gold. Another issue that I found in mineral sands is uranium can be present, but is often not particularly assayed for, and thorium itself, and Keith would recognize this as well. And the final example, or one or two more, polymetallics you have to be extremely careful with, because they compose of multiple rock types, multiple revenue streams, and frequently have waste rock issues with ARD. And each of them have to be modeled and scheduled. This is a picture of Antamina in Peru, which when it was developed in 2001 was the most expensive project in the world, at $3.2 billion, and also at 5,200 meters up in the Andes. And you can see mining just starting on to the left of the Cirque Lake over there, and that's where I was in 2001 when they just turned the first sod. Deleterious elements are frequently an issue with polymetallics, and in antimony bismuth is a particular issue. Early drilling didn't assay for bismuth, and this had to be rectified down the line. I think this final one, oxides. This is a lead zinc deposit in China, where the actual oxide and sulfide proportions were quite different and required quite different processing routes. And in much of the historical drilling, the oxide component wasn't assayed for, and led to major issues in terms of assessing the value of this particular ore body. This is a project that I worked on in 2005. It was Spence copper, porphyry copper, that we decided to heap leach incorrectly, I think, as the case may be, even though at the time the heap leach option gave us a better NPV. It was developed for $1 billion. At the time, the company was particularly concerned about developing it because of the price tag. It paid back that $1 billion in less than a year, 11 months, and it's been one of the most successful copper deposits ever developed. However, we got one thing very, very wrong, and that is the amount and type of minerals in the ore body, the leachable part of the ore body, we underestimated the amount of montmorillonite, which meant that recoveries were 5% lower than what they should have been. So even though we paid back $1 billion and it has produced enormous amounts of copper since then, we did not get it right. Hyperspectral scanning would have helped us with the definition of the clay minerals in the ore body itself. But we thought we had got it right, but we didn't. In common problems in leachable copper deposits are not sampling for acid-soluble copper. In Spencer's case, we did it right. Cobalt, which is a big issue up in the Zambian and DRC copper belt. The issue that we got wrong was the issue of mineralogy of the clay minerals, and our recoveries as a result were a lot lower. And these I've seen in many other projects that I've looked at where recoveries have been estimated. The acid-soluble copper wasn't estimated correctly or not at all. Ore bodies are different. This is my final slide on this particular section. And each of them has to be looked at in different ways in terms of the drill spacing, the drilling technique used, the sampling, and the assay itself, as has been pointed out. The Witwatersrand, just to end with one last anecdote, there's a lovely example of the Ventersdorp contact reef at East Driefontein in the middle there, running at hundreds of grams per ton. I remember in 1981, I took Andre Jodel underground. At the time, he was one of the foremost proponents of geostatistics, leading on from good work being done by Donnie Krige in South Africa. And I showed him the actual sampling technique, the channel sampling underground, and he just shook his head. It was the sampler that we chose to demonstrate it made every mistake in the book. And I think he walked away from there thinking that Harry was doing this enormously accurate geostatistics on sampling data, which was probably not really all that good. So leave you with that thought. The integrity of our sampling data often is not great. We often have to deal with fuzzy data. We often have to deal with bad data, and we have to deal with it in the best way possible, sometimes by discarding it, sometimes by just understanding it. But often we don't deal with it and we live with it, and that often does give us problems down the line. So to finish off, and I think we might have a bit of time for some questions. And what is the cost of good data or cost of bad data to us? So I've put fraudulent data up at the top because that is catastrophic, and I've used anything up to $4.4 billion. Incorrect location data, anything from 1 million lower end to 500. Incorrect sampling data, that's getting our QAQC, well, the actual data incorrect, which is the QAQC shows that it's probably incorrect, is anything up to 100 million. And I've made a guess on database integrity of anything up to 100 million. The value of good data, good location data, good QAQC, stored correctly in a recognized database, I don't think can really be valued. But it results in high investor confidence, and we measure that investor confidence often through our system of mineral resource audits, which are well established. Many of the speakers have talked about it, and what we do in those audits for everything from the drilling all the way to the resource estimates themselves, and also into the reserve estimates and mine plannings. So I'll leave you with those thoughts, and I think we do have a couple of minutes for questions. And I'm going to stop sharing my screen. Can come back if there are any questions there. Thank you very much.
Thank you very much, Matt. Are there any questions for Matt? Anybody?
Yes, Matt, it's Keith here.
Yeah, hi, Keith.
Can I go ahead? First of all, excellent talk, Matt. Always love your presentations. Excellent. And the sort of joint history we all have, when it all added together, it itself makes an very exciting conference. But one of the points I'd like to add to is your discussion of copper, total copper and acid copper. A couple of years ago, I was involved in a project on the Katangan copper belt, where they were doing acid soluble copper, but it didn't match what they were doing on the heap. The acid composition on the heap was not the same as the acid composition that was being used by the labs to determine acid soluble copper. I changed it. Do you think doing that kind of change is valid?
Absolutely. The acid soluble copper analyses that we had in Chile, we found were inaccurate in terms of predicting what we were going to get on the heap and what we get out of the heap. And we changed to what we called a sequential copper analysis. I'm not sure if you're familiar with it, it might be called something else, but to determine how much acid soluble copper there was, because it was determined by the mineral species that were present in the ore body.
You see, there was the additional issue of acid soluble cobalt, because cobalt is being extracted in the heap as well.
That
was an issue by itself.
Yeah, very much, very difficult to get an accurate assay on that.
There's a hand up.
Is it only me? Matt, I'm still sticking to 1%. That if we have good data, we could get a return on investment of 1%. Now, because our confidence in the geological model would be improved. Don't know if I've got the right words there. Can I stick to that?
Yeah, I think this is work in progress. I think that's a very good yardstick. And it might be an underestimate, actually.
Yeah, I agree.
But I think it's something that is well worth pursuing, and for collectively the industry to start putting their minds around what is the value of good data. I think, as I said earlier, probably easier to determine what value is lost through bad data, but the value of good data, I think it's really worthwhile trying to quantify that.
Thank you.
Good. Well, I think, Chego, thanks. I've got a final thank you to all the organizers. Thank you so much for putting this together and putting such a lovely lineup of speakers together. And I think it's a timely reminder, as I said earlier, of the importance of this particular subject to the industry. Thank you.